Welcome everyone to today's SEG Summit on Drone Geophysics 22. This is our fourth day of the session, and it has been an amazing conference so far. So thank you to all the attendees and the presenters. And for those who are just joining us today, this is actually the third standalone summit on drone geophysics for SEG, and it follows up on a few years of end of workshop at the end of the main meeting in-person events. And it's really developed into an amazing community event. And it's been amazing for me over the several years to see it evolve and the work that's being done. So I want to thank everybody for attending, and especially those from other parts of the world where the time zones may not be as convenient. My name is Kian Dawson. I'm a hydrogeophysicist with the U.S. Geological Survey, and I will be co-chairing with Nathan Campbell, who will introduce himself in a moment. And we have a great lineup today of talks on geohazards, BVLOS, or beyond visual line of sight, and some exciting updates on standards development. And I will turn that over to Nathan now.
Thank you, Kian. My name is Nathan Campbell. I'm with a company called EdCon PRJ, a geophysicist here in Lakewood, Colorado. And thank you, everyone. I'm really excited for today and to learn some new stuff here. I would also like to thank our sponsors for the summit. Platinum sponsor is Mobile Geophysical Technologies and Sequent. Our gold sponsor is Geometrics. Our silver sponsors are Collier Geophysics, EdCon PRJ, Geonics, Medusa, and Southern Geoscience Consultants. And just as a reminder, each presenter, and I know you kind of went over this, Kian, but each presenter will have 15 minutes and then 5 minutes of question and answer. If you go into that question and answer time, you'll hear a little chime or a ring that'll indicate that there's 1 minute left for the whole 20-minute presentation. So make sure to wrap it up by then, and hopefully before that, so we can fit some questions in. So if no time remains, we'll just scoot on to the next person. And don't forget to hit stop sharing on your screen at the end of your presentation. And then during presentations, everyone will be muted. So type any questions you have in the Q&A box. And during this discussion, then we'll have the option to unmute and to participate as well as through the chat. So I would like to introduce our speakers for this morning. Our first speaker is Andrew Mitchell. He's our keynote speaker, and he's with BGC Engineering, and he'll be talking about geohazard characterization using a UAV-lidar system. Andrew, take it away.
All right. Well, thank you for the introduction. Just to start off, a few acknowledgements here. This is work that I started during my PhD, and I'm kind of carrying on through some R&D work with BGC. My main collaborators are Scott McDougall at UBC and Megan Van Veen here at BGC Engineering. And a lot of this was made possible with funding from the National Science and Engineering Research Council and the Canadian Foundation for Innovation, along with UBC and BGC, who have been supporting this. So I am not a geophysicist. I'm coming at this from a geotechnical / geological engineering background. But when I was asked to put this together, I was kind of thinking, the geophysics approach of sending a signal out and looking at what you get back and kind of inverting either the characteristics or the structure of something within the Earth's surface. What we're trying to do here is really just looking at the signal being geomorphic changes, and then we're trying to invert the processes that are leading to those changes. So I'm going to be going through 3 examples here. The deposition and remobilization of sediment in debris flow settings, erosion driven by waves and currents in hydroelectric reservoirs, and then some examples of hill slope deformation, kind of more deep-seated, slow-moving processes. And basically how this is being done is using topographic change detection analysis from repeat LiDAR scans. So we've got this example on the left here where it's kind of hard to see, but there's some erosion and incision happening in the upper part of this channel, and then the deposition from a debris flow that came down here. So getting really nice high level of detail on these kind of things. And this is an example of what the change detection from shoreline erosion looks like. So, and I guess I should mention in both of these, our blue colors are material loss. So either generally some sort of erosion or down dropping. And then the warm colors are either deposition or material moving forward and bulging out. And then there is always some interpretation with things like this. We have our material loss here, and then it's showing an apparent positive change. But in this case, it's actually just difference in the water level from when we collected the scans. So like anything, have to interpret these carefully. Just a quick intro on the system that we've been using. This is from Phoenix LiDAR Systems. So this is a commercially available system. Part of the idea is to try to use more off-the-shelf things so that we are able to, ideally, this is things that can be picked up by other people and ran with. So we got our M600 drone here with the LiDAR scanner on it. I've seen a few other talks where people have briefly mentioned LiDAR, but if anyone's unfamiliar with it, the basic idea is you send a laser pulse out from this scanner. It goes down, it bounces off things as it travels down, whether those be treetops, low vegetation, or the ground, and then collects those. They're called echoes coming back. So from that, you can deduce the distance from the scanner to whatever it bounced off of. But then the question is, where is that distance relative to? So to resolve that, we have this GNSS receiver on the top of the drone for absolute position. And we have our inertial measurement unit to do the roll, pitch, and yaw of the aircraft. As well as all that, we have this downward facing camera. So that's collecting optical imagery of whatever we're flying over. And then the bit that's in the sky is only part of the story. We have our GNSS base station so that we can do, we do post-process kinetic corrections on this data. We have our ground station here and the communication. So we actually have a little wireless network for communication from the ground to the drone. And from our base station here, we can turn sensors off and on, make sure that there actually is data coming in, all those good things. Got the generator because this thing is a power hog. So we're kind of constantly charging batteries as we're out in the field. This is a photo from when I was still a grad student, so I was cheap labor at that time. A lot of this has been figured out with the relatively cheap graduate student way of doing things. And then finally, sky view, very important for our GPS to work properly. And we are operating this under line of sight conditions. And like so many things, all of this fancy equipment is great, but really your final data quality is going to rely on some good mission planning, good field collection procedures, and then proper post-processing going through. So once all of those steps are done, we get a point cloud. And one of the great things with LiDAR is you can parse out ground and vegetation, buildings as well, although we aren't using any of these in any sort of urban area for our applications. So this is a colorized point cloud, so kind of fusing together the optical imagery with the point cloud. And through the classification, which is done purely off the points, so it's all a geometric thing. We have the high vegetation, our low vegetation, and then finally our ground points. And it's these ground points that are primarily what we're looking at through for this topographic change analysis. So moving on to the actual study sites here, The first one I'm going to talk about is Zill, which is Mount Currie, which is in Southwest BC. So I'm down here in Vancouver. It's just a couple hours up the Sea to Sky Highway. And here we're in some kind of very rugged mountains. The rock type here is granodiorite, so quite a hard rock, but there's a lot of structures coming through here. So we get these very extensive talus slopes as, and there's also a lot of, frost weathering, things like that. So yeah, we get these very extensive talus slopes here. And there's quite a bit of precipitation here as well, especially through the winter months. So these put together tend to result in quite a few debris flows in this location. So this is one of the fans on the north face of Currie, and we got this UAV LiDAR system back in 2019, and conveniently, there was quite a large debris flow on one of these fans in 2019. So we were able to get out just a few months after it happened. And on the left here, we have our orthorectified imagery. So this is a 3 centimeter DEM. So when you zoom in, you can actually pick out individual boulders and cobbles in the deposit, large woody debris, things like that. As well, we had a pre-event LiDAR scan that was collected from a helicopter platform that was provided by the local regional district government. So we were able to combine our scan with their existing data to do this really detailed assessment of where we have erosion and channel incision, and then where the deposit of this event came out. And another great thing about this data, in the optical imagery, you can see this gray zone of deposition. And this really shows that this was a very kind of thin mud flow. We're kind of within that 0.3 meter limit of detection that we had on the change analysis. And this kind of data is great for kind of event description, and we've also used it for calibrating numerical runout models. So kind of getting back into that, how can we use this to infer more about the processes that are causing these events or active during the events. Moving along to the next debris flow site, this is at Fountain Ridge. So we're a bit further northeast, a bit further inland. So whereas Currie is a more wet environment, this is on the rain shadow on the other side of that same mountain ridge. So it's quite a bit drier. You can see the vegetation here is quite a bit lower, a bit more sparse. And what's interesting about what I'm going to focus on for this site are the avulsions that we have here. So an avulsion is any sort of fluvial system. So it can happen in rivers during floods, or it's quite common during debris flows where the flow switches the flow line, your stream changes course during the event. And that's actually how these debris flow fans build up over time. It's just this kind of stacking of these different avulsions to create these conical landforms. And what we're looking at here is one of my colleagues, Sofia Zabritsky, part of her work, she built up the catalog through air photos over a 70-year period, where we can see just how much this fan, how active this fan is, first off, and how much there has been this wandering of the channels over that time. So with this higher resolution data we're able to collect, we can really dive into some of these questions of what are the characteristics of where these avulsions actually happen. So what we're looking at here is an event from 2021, and we have this from just kind of on the ground observations. We know where channels flatten out, and when there's sharp bends in the channel, that tends to be where these avulsions happen. And if we look at this middle avulsion point from this event, we can see, there it is, there's our channel flattening, but this really helps us get a lot more quantitative on these things. And over time, we're hoping to be able to do better predictive models of where these avulsions, what the likelihood of them are, along with where we expect them to happen. Moving along to a different hazard type. This is under construction hydroelectric project in Northeast BC. And here they're at the stage right now where the river is diverted. So there's 2 diversion tunnels to allow them to construct the main dam. So those diversion tunnels do constrict the flow of the river somewhat. So we have what's called a head pond backed up slightly higher than what the kind of natural river level is directly upstream of where the dam is being constructed. And so here we can see one of these eroding faces as we have a new section of the ground that wasn't really affected by erosion processes before, but is now in contact with water. And this is a photo I took just kind of in the background of what you can see on this left image. And you can see we have these little ridges forming from the different water levels as it rises and falls in the head pond. So yeah, we have these erosional shelves forming here. And one of the great things about the high resolution UAV LiDAR data is it really helps us to capture these features quite well. This isn't a perfect comparison because our 2019 helicopter data was kind of just before they formed the head pond. But you can really see post head pond, we can pick out these erosional ridges on this actively eroding face here. And one of the things we can see is in the kind of these vegetated slopes back behind here, the point density isn't that different, partially because the helicopter platform can use a bigger, more powerful laser. So it gets quite good vegetation penetration, whereas we're getting more points just on the vegetation in this one. However, where this really shines is the exposed slopes down here, because we're able to go kind of lower and slower, and these steep slopes that are more occluded for the helicopter platform, we're getting much better data on. And from seeing some of the other presentations here, I realized my definition of low is relative to a helicopter. It's not, we aren't skimming the water, flying 3 meters off the ground, anything like that. These are generally collected 60 to 70 meters above ground. And then the final hazard type I want to touch on briefly is these slow moving deep seated landslides, which don't kind of have the same dramatic rapid impact of a debris flow, but they are very damaging for infrastructure. A lot of times, you know, we have roads, pipelines, things like that coming through these river valleys.
Andrew, 5 minutes.
Thank you. So yeah, this is our one study site here where we definitely have the landslide morphology. When we're out in the field, we can see there's kind of this downdropped block, which is giving us some indications on how it's moving. I think we just don't have the time yet to see that signal here yet. We've only got a couple of years, and I think this is moving quite slowly. But this is the kind of thing that we're looking for here. This is the 10-mile slide, another project that I've worked on. So here you see the down dropping at the head of the slide and then a bulging out at the toe. And from this, we can do a lot to infer how it's moving, the depth of the failure surface even. And yeah, a lot of good information that really fed into when we're doing the mitigation design for this. That was all very useful information. So to wrap it up, does this fly or am I just rolling in the ground for nothing? Our main advantages are we have much better resolution than what's achievable through other platforms. And a lot of this comes through the flexibility in mission planning where we can really get down and target the things that we care about. On the flip side, we only have some small areas feasible, and there is quite a bit of mission planning and post-processing effort required to do this. If anyone wants any of the things that I've referenced here, just reach out to me afterwards, and I'll turn it over to questions and just mention that do have some of the data from Mount Currie and Fountain Ridge that are available through the Pangaea online repository if anyone wants to play with the data. Thank you.
Thank you, Andrew.
Yeah, and I'll just say, Andrew, I always love seeing the data available. So thank you for doing that. So we do have a question that's popped up from Patrick. Great talk. What level of resolution can you achieve with this? Can this be used to look at centimeter level shifts as a portion of an earthen dam or a hillside starts to slump prior to an actual collapse?
Yeah, so that is one of the things we have been looking at doing, is trying to, and that last site I showed there, that's kind of what we're trying to get into. The interesting thing with with this change detection analysis is that there's a few things. You need two really good data sets. So like for the first example I showed with the debris flow fan, where we had the helicopter platform, yeah, our limited detection was around 0.3 of a meter. And that was mostly due to the resolution of our baseline scan. We're finding that we can reliably get into kind of 10 centimeter limited detection when we have two of these higher resolution data sets. And we have been doing some thinking about trying to get that down even lower. But that's still, we aren't quite confident in the kind of 5 centimeter process yet, but that's kind of what we're working towards. And I guess on the subject of resolution, yeah, that really, if you have kind of flat exposed ground, we can get kind of hundreds of points per square meter resolution, but that's never what we're working with. Kind of, yeah, these steeper slopes, just because of the angles where you can, yeah, kind of in the 10 to 15 range when we're in thick vegetation, yeah, it's usually 5 to 10 points per square meter for the bare earth. Another thing that we've been doing is also on these more vegetated slopes is looking at the trees. So kind of using our trees as a whole bunch of observation points, seeing if they're shifting, translating, things like that.
Thanks, Andrew. So we have another question from Heidi. I didn't catch if you mentioned during the talk, does your LiDAR use SLAM technology?
Yeah, so the LAN that we have isn't for the LiDAR directly, it's so that our LiDAR can talk to our base station.
And next question from Robert. Has your detection level been affected by differences in repeat survey georeferencing?
Yeah, so we have the georeferencing that we do, but also because we're trying to get basically beyond the limit of precision of the GNSS. So we actually align the point clouds to each other. So we'll take areas that aren't moving. So we're going to clip out the point cloud where we have the things that we either know have moved or suspect are moving, and we take the unchanging areas, and it's using the Cloud Compare software, or we have some in-house software to do this as well now. But basically, it will align the 2 point clouds so we get a closer match to help deal with any error from the georeferencing, things like that.
Thanks, Andrew. And I had a follow-on question, actually, Andrew, about the georeferencing. So in that unstable and sometimes unsafe environment, how are you actually getting your georeferencing in terms of, like, are you putting out ground control points? Like what is the georeferencing you're using? And how do you deal with it?
Yeah, so, and one of the things that we've been trying here is seeing how light we can get away with on the georeferencing side of things. So we haven't been putting out ground control points or anything like that, partially because, you know, on these debris flow fans, we're going to do all the effort of setting this up, and the flow will come down and wipe them all out. So what we've been doing is basically just setting up our GNSS base station, and using that as our stable reference point for each survey. And then relying on, between each survey, we have a wide enough swath that we have some areas that haven't changed, and using that for the alignment. And kind of what we've been finding also from doing this with larger areas from helicopter platforms is over time, you do start to lose a bit of precision there. And I'm not sure if that's just from kind of accumulating errors or if it's just that our older data sets are lower resolution and that's really starting to show up more. But yeah, so it's very light on the ground control. I've had the thought that it would be interesting to try like doing some more points and trying to resolve that a bit more, but only so many hours in the day, so that's the future considerations.
Thanks. And any other questions for Andrew?
I had a question for Andrew. It's kind of piggybacking on the Patrick Mises question about centimeter resolution and earthen dams. If I know you only have certain hours in the day, but I think with that system, if you were able to go like check your levels, with your GNSS base station and then like with a rover and confirm some of those levels, I bet you'd have some pretty good accuracy and you could really nail down some of that depth of penetration for like grasses and bushes and stuff. I'd be very curious to see that. And that's not really a question, but one of my questions that just came up, and I've got kind of an operator's background for drones and LiDAR, is how many flights did it take you for the M600? Like, for example, on that first area that you did, do you remember?
Yeah, so the for the Mount Currie site, that event that I showed, that was, so we get about, with the LiDAR and everything and, getting up, doing your calibration maneuvers and all that, we realistically get about 12 to 13 minutes of actually collecting LiDAR data. And to get kind of the point density that we need, it takes 4 flights to do that one fan. There's another one right over, so there's kind of 7 flights total. And with 4 sets of batteries kind of swapping out and then having the generator running to charge another set, we can get all of that done in a single day. That is now. Now that there's a bit more experience and we've kind of worked out the field workflow, but yeah, there's some sites, for instance, the Fountain Ridge. I guess it's kind of hard to get a sense of the scale, but that's actually, it's a very big debris flow fan. Well, they're 2 kind of conjoined fans. And that one, I think it takes 12 flights to capture the active parts of the fan. So there's some parts that haven't, there's one sector of the fan that hasn't been active since the 50s. So we kind of surveyed that once. And so we have the baseline in case the fan goes back to that sector anytime soon. But yeah, for what's active now is a solid day and a half in the field of fly, land, reset, do it all over again.
And what, just out of curiosity, it seems like that might be the whole debris fan areas may be perfect for drones because they're kind of small and difficult to survey. Did you have any problems finding a good place to take off or to have visual line of sight type of areas?
Yeah, there is. I had grand plans of doing more debris flow fans during my PhD, but then COVID happened, which really limited field work. And also, yeah, getting into those practicalities of places where you can take off land, you have the line of sights, not just to see the drone, but also maintain that radio link. Because I know the first time I I went a bit too far, and there was the automated voice saying radio link disconnected with $250,000 worth of stuff in the air. That was it probably took a few minutes off my life there, but yeah, it is kind of those line of sight issues, just kind of practical limitations. Also, you know, it would be nice to go higher up the fans, but then we're getting into those like really steep incised valleys, and it's haven't had the confidence, or yeah, we're kind of getting into the beyond line of sight from where we can practically take off and land to get higher up into those areas, and losing the amount of, you spend so much time getting there that you kind of start losing survey time up top. So yeah, definitely those 4 sites are kind of the ones where we were able to find good takeoff and landing spots, except for that 2021 debris flow did wipe out our initial landing and staging area, so we had to find a new one. So yeah, there's definitely those kind of challenges, and also those sites where we were also, they're a bit out of the way. There isn't any real major development on them, so we don't have the issue of the fans are kind of left to do what they will, and we can really look at these process things, whereas there are some other accessible active areas, but then there's also like the Ministry of Transportation or whatever that's going out and rapidly cleaning them up after events happen.
Thanks, Andrew. So we have another question, and I just also want to thank you for sharing some of those real world field logistics. I think there's often this misperception that we can go anywhere, do anywhere, and it's super easy. So those are really the real world realities of battery times, topography, access, and things. So Jeff asks, or comments first, Andrew, thank you for your talk. And the question is, you mentioned targeting features for movement. Have you tried debris velocity / vector direction measurement at all?
Yeah, so getting into things like the debris velocity, and if I had known I was going to have this much time, I would have brought up some fun animations. So we're always, you know, we find out about these debris flow events after they happen, because they, you know, they will occur over a few minutes to maybe kind of smaller sub events over a few hours, or a couple of days that kind of add up to these things. So we aren't able to like directly measure the debris velocity in those cases. But what I have been doing is using them for numerical runout model calibration. So we can estimate things through, like in channel bends where the flow super elevates. We can use that to infer velocities, or run up onto buildings or trees. Those are also things that we can estimate velocities from, and then try to build a model that represents those processes. For the more deeper seated slow moving landslides, again, that example I was showing where we've been doing the first couple of years of repeat surveys, we haven't gotten enough movement to really confidently pick anything up. But the advantage, the example I showed of the 10-mile slide, where that was all based off, well, we did some with helicopter and also using terrestrial LiDAR scanning. And that one where we were getting, there was a while where that was consistently moving like 5 to 10 millimeters a day. So it was a very fast, slow moving landslide, if that makes any sense. But from that, we're actually able to, look at features, because there were areas that were kind of moving as coherent blocks, and we're able to kind of track the shape of the block and how it was rotating and translating over time, which was very useful in not only looking at kind of that velocity field across the surface of the slide, but also inferring the motion, like where we're having down dropping blocks at the start, and then more translational movement, because we did have subsurface data where we could drill holes and put in slope inclinometers and see at discrete points where the failure surface was. the problem with that is the rate it was moving. We had some of them that lasted a week before they were destroyed. So for kind of that longer term, we were able to use that surface velocity field as well as the roto-translational characteristics of these discrete blocks we were able to track and use that to kind of connect the dots from our discrete points, turn it into a complete surface, and yeah, get that better sense of motion over time and kind of the marrying the surface data to what was happening, what was causing it below the surface.
So thanks so much for that great talk, Andrew. That was wonderful.
Thank you.
I am happy to introduce our next speaker. His name is Xi Yang, and he'll be talking about detection and analysis of tunnel karst by ground-airborne time frequency domain electromagnetic method. And he is with the Yunnan Aerospace Engineering Geophysical Detecting group. Xi, take it away.
Okay, thank you for the introduction. My name is Xi Yang, and I'm the second author of this abstract. Now, I come from a Chinese company, and this company's my business is as a third-party service provider to help the government with the infrastructure construction, and mainly focus on the tunnels construction. And this topic divided into 4 parts. First, I will give a brief talk about the motivation. And I believe China has the largest number of tunnels construction around the world. And in this table, I show the number of the railway tunnels and highway tunnels in China by the end of last year. And all these tunnels are in operation. And right now, more than 5,000 tunnels are under constructed, and over 10,000 more are being planned. During the tunnels construction, we may face many problems that are related to the safety. It's always very important. And here I list several of them. We have complex geological conditions and complex topography, and we may go through the earthquake zone and meet the karst landform and also the abandoned water resource area. And if we don't pay attention of this, several consequences may occur. Here I show 2 videos to show the watering rush happened during the tunnel's construction. This could cause great damage to people who are working in the tunnels. And this is only shows the watering rush. And when the water meets the soft rock, and it causes more serious disaster. And we call this muddy rush. And this video shows the muddy rush happened in the tunnel. And I believe no one can survive in such situation. So we want to solve this disaster. We want to avoid them. So a range of geophysical techniques has been used, such like the magnetic technique, like the MT method and the seismic prediction, and the GPR, and also horizontal borehole. We use this method together, but you can see most of them are implemented inside the tunnel, and only can provide limited forecast distance. And only the MT method can give a big picture of the whole tunnel area and give the whole tunnel profile of the resistivity number. And this picture below is one of the MT results we show for very long tunnel work. This has 11 kilometers long. And the blue area means a lot of water content. And yes, in the other hand, this red means there's not such water in here. And if you see very clear inside, this red bar means we give them this dangerous area, and is also at this blue area means a lot of water. And this mud rush disaster I showed above is also just happened at this area. You can see it's happened in this high water content area. And then here is another example for the empty method. And this profile is has been done before the tunnel constructed. And we can follow when the tunnel is digging. And this small square shows that the water erosion events happen, and we can verify our results with this empty method. And it's quite happened. This water erosion is in this blue area, which means this method can provide some information for us to keep our building, our tunnel building safety. And this is, in most cases, if we want to figure out the geologic condition in this tunnel area, we may need several survey lines. This picture shows we used 5 lines to look at this geological condition in this tunnel area. But we need to move our equipment into this right place to get our data. But sometimes this is very difficult for people to climb. Even people is very hard to climb. It's also very difficult for people to carry our equipment up to this mountain. So this is our motivation to use this drone techniques, because this is very efficiency and also very safety. People do not need to climb this kind of mountain. And compared to the helicopter techniques, it's relatively inexpensive. Okay, this is our method. I can explain this in detail. We mainly based on the difference of the resistivity number, and especially for the water, because the water is quite important for our tunnel construction. And here I list in this table several numbers, average numbers of different rocks. And this is our method, the principal method of our method. Why we call them time domain and frequency domain? Because we use we actually use 2 different domain. At the sorry boss, this Chinese character. At the near this our source is on the ground, and the receiver is on the air. And the near distance is like the the picture the right hand side. We use the secondary induction signal. It's quite like the TM method. And when the receiver is far away from our source, we use the continuously transmission current, which is we continue give our source power, and we collect the magnetic field in the air. And this is very like the audio geomagnetic method. And this is our equipment. We have our source, and it's quite large. We need to truck to carry them. And we have our drone carry our receiver. And we have our source with multi frequency waveform. And this is the main parameter of our instrument. And you can see the power. and it's quite large power, and this also of the current is quite large. Okay, and the next is a case study. The tunnel we give our measure is located in Chongqing city, and this city also has a nickname called Mountain City. And this red shows the mountain. The 75% of this city is mountain. And here is the tunnel located area. A lot of water around this tunnel, which means a lot of water supply. So it's could be very dangerous if we do not pay attention of these waters. So this is the setup of our survey. We have our source on the ground, and it's have 5 kilometers away of our receiver line. We have 5 lines of the receiver, and you can see right. This picture shows our 5 lines, and each lines have 100 meters away from another. So this is how we do the measure. We have thought a lot of method to increase the contact area. We dig a hole and to also use salt water to into this hole. And this is our frequency table. We have 4 groups of frequency, and each group we collect 5 different frequency. And this is how we deal with the data. We measured the magnetic field in the air, and then we also to do some denoising. And yes, I'm not go very detailed about this. And we also, at the end, we also need to do some correction of the depths, because the topography is quite influence our final results. And this is the inversion results of our 5 lines. Yes, I showed all of them. This is the 3rd one, and the 4th one, and this is the 5th one. And we have the 5th inversion results. We can give them a quasi 3D dimensional results. Also, we have combined our geological survey. Okay, we also make MT survey at the same area to compare each of different results, and it shows quite similar results. We have a high water content area at the bottom of this mountain. So I give a summary of my presentation. We tried the drone technique to give our electromagnetic results of the mountain to show the high water content area. And this technique mainly can detect the groundwater and the fault zone. Also can detect the metal mine, because this based on the resistivity difference, and the depth could be goes to 1.5 kilometers. And this technique is very efficiency. It's 20 times higher than the ground method, and also it's give our a mind of engineering construction, and also can use this to mineral exploration. Okay, thank you.
Thank you so much.
Thank you for the talk. So this is from Michelle. Thank you for the talk.
Okay.
and for the video examples, do you know the shutoff times that your system is working with?
I don't quite understand this. What the shutoff time means. For the case study, we have very large distance between our receiver and our source. So basically, we use the frequency parts of this method. So the source is continue supply the signal. So I think there's no shutoff time for this case.
Do you ever use a signal that's like positive, negative, so to speak, where kind of like a square wave?
Yes, a square wave.
Okay. Is that what maybe she was asking about, or I'm not sure, but it's never off. It's always, the signal's always on, right?
Yes.
I'll piggyback on that with a question. What speed, if you know this, what speed does your drone have to fly to collect?
Speed is depends the signal receiver. If you want to collect high quality of the signal, you may very slow speed.
Okay, yeah, like probably what, 2 meters a second, 3 meters a second, something like that.
Yes.
Okay.
Thanks. The next question comes from Jeff.
Okay.
Thanks, Shi Young. Very impressive work. Is your modeling 1D or 2D or 3D?
Our modeling is 2D because we have 5 survey lines, so we can use 5 2D to get a fake 3D, but it's not 3D.
Thanks.
Were you out there in the field when you collected?
Yes.
What was the wind like? I mean, really what I'm asking is, does wind blow the sensor around? And if it does that mess up your signal receiver?
Yes. The wind and the way of the drone flying can influence our signal. So we need to after dealing with the data, yeah, we need to do some correction.
Did you have to refly?
Yes, of course, yes.
Okay. Yeah, it seems like really difficult topography, even for drone, so I can imagine that being pretty challenging with wind and with steep topography changes.
Yes.
We have another question. Jeff asks, can you tell us a bit more about work for mining?
Actually, we do not use this tech for mining because yes, our company is mainly focused on the construction, engineering. But we think this tech should be also useful for mining industry. Yeah.
Well, Xi, thank you so much for bringing this newer technology to light. Very impressive stuff.
Okay, thank you very much.
Fanni Kodas, if you are there, I'd like to introduce you, and you're going to talk about high-risk slope monitoring with drone-borne multispectral data. Fanni, take it away.
Okay, so welcome everyone. Greetings from Hungary. Today, I would like to introduce you the case of Szent-Mihály Hill at Danube Bend, North Hungary, and the problem with its high-risk slope that we monitor using drone-borne and multispectral data. Our study area located in northern Hungary, where the Danube River splits the North Hungarian range in 2 sections, creating a water gap between the mid-Miocene and Andesitic volcanic hills. Here, the area is deformed by an active uplift, which just fastened the incision, and this increasing incision rate can cause continuous landslides. It's important to point out that this hill is quite unique in Hungary because it's got a radial pattern and a very special geometry with very mixed material, very various mass material. For example, on the bottom of my slide, you can see the 3 major accidents that was taken place here in the last decade. And the first 2 in 2012 and 2020, it was both a rock slide with quite a big amount and big size rocks. And surprisingly, this year in June, there was a massive mud flow that we weren't aware of. And it caused a lot of problems because the national railway and also a major road goes here. And because of the unique geometry, I can show you, as you can see, here goes the railway. And this is just one road and one railway. There is no way out. So the major problem is that when this kind of events happens, there is we don't have any escape ways. So it's so dangerous for human life. And because this is a very popular tourist destination too, it's very important to be aware of the most hazardous places and to make quite predictable these events. Because, for example, in the Alpine, this is quite a common case, but it's absolutely a unique thing in Hungary. And unfortunately, these accidents happens more and more times during the years, because the increasing in season indicates that these events will be more and more times in the future. Here you can see we had several UAV flight campaigns, and on the picture on the right you can see that we already have protective walls too. But when a certain accident happens, the mass can exceed the capacity of these walls and overflows on the hill, and just every mass flows on the railway and the roads too. For our measurements, we took ground control point measurements that was defined with RTK GPS to reach a centimeter to reduce the error under a centimeter scale. Some major parameters about our last flight campaigns. Our total covered area was almost 1 square kilometers, and we took almost 400 photos with an average of 191 meters of flying altitude. It's important to point out that the measurement was taken place in February, so it was a leaf of season, which is important because we would like to build a model. And in the leaf on season, the trees and the vegetation with the leaves can put an error in our elevation model. So we just wanted to get rid of this kind of error. So we took the measurement in leaf of season. Our first goal was to create a DEM, a digital elevation model. For this, we use the Agisoft Metashape Professional Edition software, which is a standalone software product that performs photogrammetric processing of digital images and generates 3-dimensional spatial data to be used in GIS applications. Our main problem was the positioning of the ground control points, because you can see on the picture on the left, the little blue dots shows you all the ground control points that was placed on the field, but it's all on the road because these slopes are very steep and it's quite dangerous for a person to climb up on the hill. And on the other hand, these slopes are in constant move that can occur an error between flights, because when we go back half a year later and do the same measurement, the ground control point can be about 10 or 20 centimeters away from the place that we just marked with the GPS before. And that's why we just placed all the ground control points on the road. So our next goal was to get a run of modeling from our final digital elevation model result. And here you can see our run of calculation. Our calculation was made via Saga software, and we mapped the drainage system. The designated catchment areas by defining 4 points. We can define the 4 points. It's easier to identify these points because of the radial pattern. And after we get these points, the software just calculated all the area collected to this 1 point where all the water, all the rain pours into that 1 point. This is why we call it 4 point. At the end, we could find more than 300,000 square meters of potentially hazardous areas. And I would like to highlight the 3 major catchment areas over here. Or you can see the picture on the right, that these 3 major areas are centered in the middle, where the actual accident this year, the mud flow, was taken place. So I think it quite good correlates with the things that we can see and experience in real life. Our next goal was to improve the resolution, because high quality processing requires quite huge computer capacity. I wrote an example for you. So you can see the medium quality processing makes 8.5 million faces. But if we want to do this in high resolution, it will create more than 30 million faces, which just really requires huge computer capacity for us. So our goal was to optimize the research and the quality ratio by multiple processing mechanisms, and then we just compare the results. Here is the difference between the medium on the left and the high quality processing on the right. I think it's so much easier to locate the poor points and to locate the catchment areas too, which was quite interesting for us, that at the end, at the high resolution processing resulted less catchment areas in total. And there were some poor points that just couldn't be marked on both results. For example, on the left here, we couldn't mark the same catchment area than here because it hasn't existed anymore. But over here, another catchment area just showed up. That shows that the high resolution has quite accurate results. I would like to highlight the major catchment areas here too. And it's quite interesting because at the medium resolution, there are 3 major catchment areas. But if we do the same processing with the high quality, the 2 areas on the left just merged and became 1 major catchment area which is the most hazardous part and the most landslide risky part of all the hill. So this is the place that needs some preventing dispatch. So what is our main goal of our study? We would like to make continuous monitoring with drone-borne pictures and compare each year's and each measuring's results, find the differences and the changes of the catchment areas. And this way, if we observe the high-risk areas, we hope that we can make these kind of accident-causing events predictable. This way, if we predict the location of hazardous events, we can save life, keep the traffic going, and etc. For our plans for the future, we would like to take several multispectral data too, because we would like to monitor the water saturation of the slopes and see if it correlates with our catchment areas and the hazardous points of the hill. And on the other hand, we would like to investigate the condition of the vegetation too. Because of the active motion, the vegetation is quite sparse and it's moving down. And this way we cannot really plant protective trees that can protect the railway and the roads from a massive mass movements. But our hope is if we keep on monitoring, we can come up with an idea to save the vegetation over here at Szent-Mihály Hill too. So thank you for your attention. And if you have any question, just ask.
Thank you, Fanny. Great talk, really interesting stuff. I'll pass it on to Kian here and you can do the Q&A.
Sure. Thanks, Fanny. We have one first question from Tom. Thank you, Fanny, for a very interesting talk. Can you tell us why these events happen in midsummer?
Gladly. In Hungary, the most rainy part of the year is in midsummer, mostly in June. And this way, the weather can really take a major part in these landslide effects, because after a heavy rain, there is a bigger opportunity for this kind of landslides.
Thank you. The next question from Coit, and I apologize, Coit, if I'm pronouncing that incorrectly. Why did you not break the catchment areas automatically or semi-automatically at the highest measured ridgeline in between two of them or between others?
It's an interesting question. We already think about this, but this whole study is in the beginning status, and we just wanted to do this way to see if it works. But thank you for the question. This needs some future studies.
Thanks. Other questions? From Nick. Great talk, Fanny. Was your higher resolution processing also undertaken in Agisoft Metashape?
Yes, it was taken in Agisoft Metashape, all the processing except of the runoff calculation was undertaken in the Agisoft Metashape software.
I have a follow-up question to that. I was curious, I was really interested to see the analysis of comparing the high resolution versus the medium resolution. Did you also consider the number of images you're taking?
Yeah.
And is there a recommendation of, can you get the resolution you need with fewer photos?
I don't think there is any recommendation. I just have to say the more the better, because this picture have at least 60, but in better cases 70% of overlapping. And if these are in these pictures, the software finds the similar points and creates a point cloud. And that's why the more the better, because if you have more pictures with more overlapping, the software will find more similar points, and they can be sure of their position, because every point has their own position, X, Y, and Z.
Thank you. Another question from the audience is, what drone platform did you use for data collection, and were the flights automated or manual?
Thank you for this question. I don't exactly know the name of the software we use, because we already tried more softwares for this. So I don't really know for this exact measurement what we used, but it was an automated flight. We just set all the way for the drone to fly, and the drone just came back when it was finished or when it needed a battery change.
And I think part of their question was, what specific drone were you using? Like the drone itself? Do you know the name of the drone?
We tried several drones, and for this exact measurement, I think we used the DJI Mavic 2. I'm not sure, but maybe we used that one.
Thanks. And so there are a few other questions. Maybe you can answer them in the chat itself, because I think we are heading into our break. So this was a great talk, and I want to give a round of applause, a virtual round of applause to all our speakers, to Fanni, and to everyone who's spoken so far. We will have a 20-minute break right now, so we will return at 1:15. So thanks, everyone. All right, welcome everyone back after the break. Our first speaker for our next session will be Dan Bochicchio from Tetra Tech, and Dan is going to speak to us about BVLOS, Geoscience Beyond the Horizon. Take it away, Dan.
All right, thank you, Ken. And let me first say thank you all for taking part in this entire summit. We've had a lot of really interesting and very inspiring talks, both in the technical and the theoretical. And I'm going to be more on that theoretical side for this presentation. While I am a geologist, not a geophysicist, I can appreciate all the amount of work and progress the geophysics community has made in advancing drone technology and bringing these applications to our field and having some real impact. So with that, I'll just jump into my talk. And what I'm going to be talking about is this ambiguous title of Geoscience Beyond the Horizon is to point at that I'm going to be talking about the current state and future states, potential future states of regulations and technology that enable beyond visual line of sight, or what I'll just refer to as BVLOS from here on out, flight capability. And jumping into it, I'd like to start with this little quote from Arthur C. Clarke, who was a futurist and science fiction writer. The only way to discover the limits of the possible is to go beyond them and into the impossible. So a lot of the work that we do, look back 10, 15 years, seems like science fiction, kind of like this geostationary orbit that Clarke wrote about, that they then named after him after it became real science. In that center little animation, you see a Skydio drone semi-autonomously inspecting a bridge from below, something that we wouldn't have thought would have been capable a few years ago. Now we currently do, and get beyond visual line of sight waivers to do that. And on that right image, you see something that really does look science fiction, an augmented reality heads-up display for drone pilots to see multiple screens of data while still observing their drone in flight. And that's real. This is a real piece of technology. So with that, I just want to put a little disclaimer out here that I'm going to be talking about regulations that exist for the FAA in the United States and applications in the United States. And that's specifically because there have been BVLOS operations all throughout the world that are very successful, but in the United States, we have a pretty strict and limited scope for that BVLOS definition. And we also have pretty narrow regulations for our national airspace system. So with that, let's just talk about something we've probably all seen and are familiar with, Part 107.31, visual line of sight regulation. Now, we all understand what we're supposed to be doing as pilots and adhering to these rules. But if we look at what a BVLOS waiver really does, we can kind of redline certain aspects of this regulation, where if you were to visually see with the unaided eye the aircraft during operations. Now we just refer to it as to be able to communicate with the aircraft and also the rest of the operations team. And there's a big emphasis on that third rule there, to observe the airspace around the aircraft while it's in operation, and also to be able to inform the operator what sort of air traffic hazards there could be, non-participatory manned aircraft in the area, or perhaps birds. That's another way of saying aerial obstacles. So with this in mind, let's talk about what BVLOS really is. And there's some misconceptions here, because the main objective while flying the aircraft, like I said in that third part, is to detect and avoid certain obstacles in the air. Now, with this comes from rules designed for manned aircraft, where the pilot sitting in the cockpit can view their surroundings somewhat in 360 and detect other aerial obstacles and avoid them and come up with an avoidance maneuver. So in order to do that, effectively do the same thing with an unmanned aircraft, we have to think about what really is beyond visual line of sight and how do we attain that detect and avoid system. So in this diagram, you can see where obviously there is visual line of sight from pilot to aircraft, and there's also what this misconception is for beyond visual line of sight when you go past that envelope. So when people, in the past year, there have been dozens and dozens, almost every day, there's a new beyond visual line of sight waiver granted. And the misconception is that while the pilot cannot visually see the aircraft, they are able to communicate with an observer who can witness the aircraft and see its surroundings. But that's what we consider extended visual line of sight, or EVLOS. And while the waiver, you can look at these that are granted online, the waiver does say it is a BVLOS waiver. We want to try to define what is true BVLOS, especially for geophysicists who want to go BVLOS with their operations. And we might be flying at lower altitudes, or maybe looking for that price point that doesn't actually involve putting more boots in the ground, those observers, to see the operation while it's happening. So some technology that allows for quote unquote true BVLOS are things similar to traditional avionics, like this radar system. And we'll talk a little bit more about these technologies as we go on. There's also a more novel approach, which is multi-directional acoustic sensing to look for sounds coming from other manned aircraft in the surrounding area. It's a little less used, but the one that is most used now is a visual-based system that combines machine learning and computer vision and partial AI to detect its surroundings. So we'll talk about that technology a little bit more, but I want to give you some examples of what quote unquote true BVLOS really is, where it's been used in the field. And for the interest of time, I won't dive too deep into these subjects, but you could look into American Robotics for their really essentially a drone in a box solution where there is no pilot, complete autonomous operations of that aircraft for asset inspection, be it for utilities or agriculture or even defense. Another great example of true BVLOS is designed by Iris Automation. They're the ones who designed this Cassia AI-driven visual observance system. So as you can see, there's the Cassia ground system, which is that upper photo, which is a series of cameras that view in 360 the airspace surrounding that flight corridor. This essentially acts as a visual observer on the ground who can provide situational awareness back to someone sitting at a desk in front of a computer. And the AI system there is able to assist the pilot, the remote pilot, which is truly remote. And there's also the same system design on the aircraft. So they use this for search and rescue along a river channel. And what this really means is that you're not only taking people away from the field during operation, but you're providing immediate deployment, real-time insights, and faster response, which equates to dollars, time, and even lives saved. So the real common denominators there are listed there. where you have complete situational awareness. There's still a human in the loop into making decisions for this entire process, while there is some automation to do things such as avoidance maneuvers to eliminate the chance for mid-air collision. There's still a human there making decisions. Now, I still have a lot more to go through, so excuse me while I kind of gallop through some of the regulations, talking about some of the technology that enables that BVLOS application, and really we'll drill down to the why, like why geophysicists are really interested in BVLOS operations. So there's a lot to this diagram here, but I think the title there, the Wheel of Suffering, is really what describes it best. That, you know, even in military applications, it took decades to be able to get the technology to meet regulations and regulations to agree with the safety components of that technology. So since the industry is really calling for BVLOS, you know, whether it's transportation of goods or scientific applications like ours, there's a aviation rulemaking committee that was formed in 2021 to essentially guide the FAA to allow for some division of BVLOS. And essentially, they came out with, in their report in March 10th, is the suggestion for a Part 108. So this would allow for new operating rules, new certificates for pilots to get to be qualified to fly BVLOS at their own discretion, but it comes with other requirements such that are more aligned and akin to traditional avionics, such as third-party service providers for equipment repair, equipment inspection. Really, you start thinking of insert label as a service, so radar support as a service, or software support as a service. So this arc has really opened up the possibilities for what we can do with BVLOS, and I think it's going to change things quite a bit coming in this next year. So really the way to think about or to consider going into BVLOS is to put yourself in the shoes of the FAA, where they consider the small unmanned aircraft systems to be the least amount of flying that actually happens in the national airspace system. So it also allows for the most acceptable risk. But as we start increasing the number of small unmanned aircraft flights, we have to start accepting more risk mitigation. So while technology may provide more safety, it doesn't really provide amnesty for getting past and waiving certain regulations. We need to consider it all as one. So the way the FAA and even NASA has considered this is it's, you know, there's a lot of text here, but for the interest of time, we'll just talk about this as setting. So setting, you know, location, 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 it's all about what sort of risk you imply by the setting or area that you're flying over. In these cases, you can see that complexity increases as you go from agricultural, you know, the potential to crash in a field is a lot less risky than the potential to crash into infrastructure, which could harm the livelihood of people. And then flying over suburban areas, that's, you know, obviously much more risky. So this is the way that the FAA is trying to consider this, where there have been different regulations that regulate the aircraft, the operator, and the airspace. In order for drones to be integrated into the national airspace system, we have to consider them all concurrently. Now, I only have a little bit more time left, and I really do want to get some of your questions. So I'm going to talk about the 3 different components of technology that enable beyond visual line of sight, that being the navigation systems, the platforms in which are flying beyond visual line of sight, and the communication systems that allow for that. So when it comes to navigation, I've kind of broken this up into what is terrestrial, how do you navigate close to the ground, essentially avoiding impacts with the ground, and how do you navigate in the air, so avoiding impacts with other or potential impacts with others using the airspace. So like I said, one of the most important things is detect and avoid. So how do we detect the ground? How do we also detect other aircraft? There are great radar systems that can sense down to the centimeter moving objects, not just stationary objects, but as you have different environments, be it crashing waves or swaying trees or bushes, this particular Einstein radar system I've seen enable fantastic results for people to fly low and slow to the ground. And we can't forget about our SPH engineering friends who have developed the laser altimeter. Produces similar results, but I would have to say that there are different technology for all kinds of different situations. And the same goes for aerial detect and avoid. This is a subject that has really developed a lot in the past couple of years, and I think there's still a lot more room for it to grow. Because I'll talk about remote ID in a little bit, but the effect that we want to have with aerial detect and avoid is really to keep removing the people, the boots on the ground, and start inserting technology that mitigates that risk and can effectively do the same as the person. And so going down, when it comes to mission planning for data capture, we have a whole suite of GIS tools that I think are really helpful to us. Esri's ArcMap even has a drone component for designing flights, but also processing the data that comes from it. And I think there's a lot of communities in the Python world that are developing tools that can help us not only design or more automate the process for data capture and assuring good mission creation, but
Dan,
also,
5 minutes, just a heads up.
Thank you. I'll keep moving on. So when it comes to that's for designing your data capture of terrestrial objects. But for the actual flying itself, I think there's, UGCS is a pretty universal software that has been making great strides in including other software packages and hardware packages into their system so that it's become pretty seamless and easy to design these BVLOS flights. There's even Mission Planner, which is a little more rudimentary and actually in some ways more robust, but it's for more advanced users. And I'd even throw this one out there that there are some groups like Hammer Missions that have been designing more user-friendly software for doing that mission planning. Now, when it comes to platform, this is one that people get a lot of questions on. What kind of aircraft should we be using? And you really can boil it down to there's the fixed wing type and the multi-rotor, as we all know. And if you look at the pros and cons of each, they're just completely flipped from each other. I think the way to think about beyond visual line of sight operations with respect to your platform is what altitude are you flying? What is your sensor data capture rate? So essentially what speed can you fly? And what is the weight or size or power requirements from that aircraft, from your sensor, I mean. So MGTOW, the max gross takeoff weight, is a real consideration here for fixed wing operations. I think there are some geophysical sensors out there, such as Stinger types or even slung load or tail end sensors that can be applied here, but I would really lump fixed wing operations and BVLOS to high level screening. So perhaps using a magnetometer to look for large ore bodies, which is something that could replace the manned aircraft for a smaller amount of money, essentially. And in the multi-rotor realm, it's becoming difficult to make those two things meet of the maximum gross takeoff weight and your altitude and the speed at which you need to fly. So I think there's a lot more flexibility with multi-rotors in that space, and there's a lot more room to improve on that. But you do have the lack of flight time, usually, like we were seeing from some LiDAR demonstrations earlier, that it can take up to 18 flights just to complete survey of an area. And to go beyond visual line of sight, that is something that needs to improve in the future. And I think the technology is coming. Getting close to the end here, some of the communication technology that exists, like I said, there's this new rule that starting back in September of this year, aircraft providers and manufacturers needed to provide a solution for remote ID, essentially FAA's way of putting license plates on all drones that are flying in the sky. So come September or October of 2023, this will be a requirement for all pilots to be transmitting and broadcasting their position, their essentially their flight parameters as they're in flight. And something that's really changed this idea is the availability of using satellite connections or 4G LTE built into your drone operations, so that you're not just relying on command and control to come from your radio direct line of sight radio frequency, but instead with a mobile network. So this is really going to change things, not just for remote ID or the ADSB, the automated distribution signal broadcasting.
1 minute left, by the way.
Okay, thank you.
You bet.
So I think this idea of mobile network connection is really going to change things in the BVLOS world, especially since there's even adapters being created for retrofitting some aircraft to allow for that. And moving towards the bottom left, looking at advanced ground control stations, I think there's definitely room for that to be a third-party service where you go out and you design your flight as a scientist, you know what you want to collect, and you get a third party to help you actually conduct the operation. So this kind of opens the question of what sort of next gen systems on chips or internal navigation systems are going to be out there. And I don't want to cut into our time for questions, but in this slide, I want to point out that autonomy is key and essential for us to be able to do beyond visual line of sight work as geophysicists. Like I said, flying close to the ground is a challenge, but
Dan,
that's where autonomy will fill in.
Dan, I'm sorry, I'll have to chime in here. Yeah, that was our time for questions too.
Oh, sorry.
So that's okay. There was one question in the Q&A. If you'd like to just go into that, and you could answer that.
Great.
But we are going to need to move on
Yeah.
to our next talk.
Okay.
And I'll remind everyone that we'll have a discussion at the end. We have an hour set aside, so folks can post your questions for Dan in the Q&A and also stick around for a longer discussion. So Dan, if you want to, that was great. Thank you so much for the talk. And I'm sure there will be a lot of discussion later. So if you want to stop sharing, then Stephen can queue up their slides. So our next speaker is Stephen van der Veeke from Medusa Radiometrics, and Stephen is going to be updating us on the Near Surface Geophysics Inter-Society Committee on UAV Geophysics Guidelines and Standards, and the progress, providing a progress report. So take it away.
Okay, so good morning or good afternoon. Welcome to this presentation with the title NSG Inter-Society Committee on UAV Geophysics Guidelines and Standards. Guidelines for drone-based radiometrics, electromagnetics, and ground-penetrating radar. And I'm going to present the progress report. And it's a pretty long title. However, it describes the main purpose of this presentation. In the next 15 minutes, I will make the case for a committee that drafts guidelines for the implementation and data processing techniques needed to use geophysical methods, measurement methods on UAVs. My name is Stefan van der Veeke, and I'm a member of this Inter-Society Committee. I have a background in radiometrics, acquired partly as a researcher at the University of Groningen in the Netherlands, and partly as an R&D engineer at Medusa Radiometrics. This is a company that manufactures gamma-ray spectrometers and develops the software needed to analyze spectral data. Both positions I have a focus on UAV-borne applications. So my research field is UAV-borne radiometrics, and my main development efforts are directed towards the next generation of gamma-ray spectrometers that can be used on UAVs. The committee that I'm talking about formed after, I think, the first summit on drone geophysics held in the fall of 2020. At this summit, the progress in UAV-borne geophysics became very clear. And this was, I think, one of the first times I was involved in such a large group of people working in this field. And the general consensus at this meeting was that we live in a very exciting time where the emergence of off-the-shelf UAVs and measurement equipment allows new applications of geophysical measurement techniques. However, it also became clear that there was still a lot of work to be done before the widespread implementation of these techniques could be established. Many researchers and pioneers in the field have faced similar problems and hurdles to overcome. Therefore, it was easy to conclude that a form of collaboration and sharing of knowledge would benefit all involved and future parties as well. So the slides I'm now showing list a group of people that voluntarily signed up for this committee, and they have the intention to promote the widespread implementation of UAV-borne geophysics. And as shown on the slides, this group of people have a large set of affiliations and also represent a large number of institutes and companies working in this field. So the first question that could be asked is why would we need a guideline for UAV-borne geophysics? Especially because many guidelines already exist. For instance, the ground and airborne measurements generally are available for quite some time. And the answer to this question is that UAV-borne measurements are in some aspects significantly different from the conventional implementations. There was evidence that a significant portion of the data collected in these surveys is of a different quality than the geophysical industry is accustomed to. And this difference in quality needs to be addressed for the benefit of the reputation of the geophysics industry, and also for the protection of the clients paying for drone geophysical services. Unfamiliarity by users of either the limitations of the physics or the differences in data processing or the legislation risks that are involved in UAV-borne surveys can harm the reputation of all geophysical technologies. Bad data gives our industry and profession a bad reputation. Therefore, the substantiation for such a guideline is more or less the main message of this presentation. The goal is to establish a best practice, which is a set of instructions that are known to produce good outcome if followed. At the same time, the limitations and opportunities of these techniques are established in this guideline, and they dictate a realistic expectation and a sense of quality control for the results of these geophysical measurement techniques. So that now we have a clear view of the why, I can present the how. So, and it's clear, as was clear from all the presentations given in the last couple of days, and even the presentations in the past summits, we can conclude that a lot of experience and knowledge is present within the community of users of UAV-borne geophysical techniques. Therefore, it was not hard to establish an approach for drafting these guidelines. They are a community effort. The guidelines and standards from the conventional ground and airborne approaches are used as a starting point and updated or amended with methods from peer-reviewed literature and with the experiences of operators in the field, so that we can establish a UAV-borne specific guideline. There has been made a conscious choice to establish a guideline and not a standard, because guidelines can easily be developed and readily updated, which is much more suited to the rapid evolution of drone-based geophysical technologies. Standards are more difficult to develop and get an agreement on, but as these guidelines and technology matures, these guidelines could be developed further into industry standards. Until that time, with industry self-regulation and clients demanding quality data, these guidelines can serve as a de facto standard. All drone geophysics guidelines that result from this committee are work in progress and are being framed, drawing together the experience of the committee members and reviewers, as well as both recognizing and referencing the rapidly proliferating literature on drone vehicles and data processing techniques described in literature. So in conclusion, these guidelines are a community effort and will be updated continuously based on the latest developments. So drafting a guideline for UAV-borne geophysics is no small task, taking into account the wealth of techniques that can be implemented. Therefore, a set of topics to be included in the guideline were discussed, and a common agreement reached that the first effort should be directed to developing a guideline for these techniques listed on the slide. For each technique or sensor, a subcommittee was established, and those techniques and subcommittees that are now being developed are magnetics, radiometrics, electromagnetics, ground penetrating radar, and ideally also gravimetrics. Of these techniques present in the slides, the magnetics guideline is in the most mature state. In fact, the presentation after my presentation, given by Tim Archer, will outline the contents of the first release of this guideline. In addition to the main techniques, several subtopics have been identified that have an importance to each measurement technique. These topics are developed in parallel to the main technique and, where applicable, included in each main technique specific guideline. And these topics include the UAV-borne platform, positioning, GPS, RTK GPS, the safety aspects, supplementary sensors with your measurement, and survey planning and execution. And since Tim will present the magnetics guideline after this presentation, I won't be expanding any further on this topic in this presentation. And now in the final part of this presentation, I will give a short status report of the other measurement techniques listed on the slide. So the Radiometrics subcommittee has drafted the first version of the guideline for UAV-borne radio element mapping. And this guideline has used the IAEA guideline for airborne radio element mapping as a starting point. And the measurements listed in this guideline were critically reviewed for the applicability in UAV-borne guideline and, where possible, adopted with a UAV-specific modification. Practices that were not directly transferable when using the UAV, like height and radon corrections, were reviewed, and new methods are suggested using peer-reviewed literature. The radiometric guideline aims to cover all the steps needed in UAV-borne gamma ray surveys. This includes the preparation, execution, and data processing steps. An extra emphasis has been placed on the preparation steps of a gamma ray survey. Among these steps are the selection of a detector in terms of size and material. And the second very important step in the preparation is the development of a survey methodology. By adopting a low flying height or small grid line spacing, smaller detectors can be used, which is beneficial for the UAV flying time and maximizes the quality and quantity of the collected data. This methodology also includes the effects of the footprint of the measurement and how this affects the interpretation in the data analysis steps. This guideline then for radiometric continues with the quality control before and during the survey, and finally the data processing steps needed to derive the radionuclide concentrations from the recorded spectra. These latter steps include some processing steps that are significantly different for UAVs compared to the conventional gamma ray measurements. Height corrections to correctly establish the absolute radionuclide concentrations in the ground, and radon corrections that differ from the conventional procedure. This guideline, the radiometric guideline, is in a stage so that experts in the field can review the draft of this guideline. The list of experts consists of manufacturers of gamma ray spectrometer, users with experience in implementing airborne and UAV-borne gamma ray surveys, data analysts with spectral data analysis expertise. And we are still looking for volunteers for reviewing this document. And we expect that the first publicly available draft of this guideline will be published somewhere early 2023. Now moving on to the ground penetrating radar. In the recent years, miniaturization has enabled GPR instruments to be carried by medium-sized UAVs, with consumers attempting to employ airborne radar for diverse tasks, ranging from mineral exploration to underground utility mapping. But the governing physics suggests that this technique is most effective in specific environments and will generally produce significantly inferior data than ground-coupled radar. Although there are specific use cases where airborne acquisition is logistically advantageous. Furthermore, in the US, Canada, Europe, and even elsewhere, specific legislation limits the use of GPR within 1 meter of the ground surface, so thereby restricting the UAV to very low flying acquisition. Unfamiliarity by the users of either the limitations of the physics or the legislation risks harms the reputation of all GPR technologies. The GPR subcommittee is developing guidelines for the use of UAV-borne GPR with recommended instrumentation and data acquisition parameters, as well as processing steps specific to UAV-borne acquisition. These guidelines will consider legislative restrictions where relevant, And it's expected that the initial draft of the UV GPR guideline will also be available in early 2023. And finally, the EM, the Electromagnetic Subcommittee. They are preparing a guideline for both UAV-borne frequency and time domain electromagnetic systems for resistivity mapping of object location. Existing and potentially emerging UAV EM systems employ either a transmitter loop and a receiver located on the UAV vehicle, or multiple vehicles, or with a static ground-based transmitting loop, or grounded wire and just a UAV receiver, or the other way around. For the EM subcommittee, it's expected that the initial draft of the UAV EM guideline, which takes into account the legislation as well, will be available somewhere in the fall of 2023. And this brings me to my final 2 slides. And here I would like to restate one very important aspect of all these guidelines, which is more or less the main message of this presentation. And that is, these guidelines are a community effort. And this community effort is twofold. First, it's directed to the users, the industry, because they are urged to refer and to promulgate these guidelines for UV operators that implement these techniques to study and follow them, and for clients, for their own protection, to require that UV operators follow and demonstrate adherence to these guidelines, and for interpreters to educate themselves about these guidelines when ascertaining the provenance and quality of the UAV-borne collected data they are analyzing. And secondly, the second step of this community effort is that we are looking for experienced users to voluntarily offer their contribution to the further development of these guidelines, either as a reviewer or a writer or a counselor. Once again, on this final slides, I list the expected release dates for the subcommittees and their guidelines. And I want to end this presentation with a call to the audience. So if you are interested to contribute or simply want to receive more information about these guidelines that are being drafted, please contact me or any other committee member listed on this slide, or anybody you might know, because we are really looking forward to the community and their help. And with this, I would like to end my presentation. Thank you very much for your attention. And I believe there's some time for questions if they are in the audience.
Indeed, thank you. I'm guessing there are going to be a lot of questions and follow-up. I guess I'm curious if you could speak to sort of what you're seeing as the greatest challenge in developing these, especially given the range of applications and the range of flight conditions. For example, that the optimal flight conditions for a magnetic survey, for example, that's kind of doing bump finding for, abandoned wells or, underground storage tank would be very different from magnetic surveys for fundamental geophysical mapping. And how's the team? Is that turning out to be a challenge or not?
Yeah, actually, I think that's the biggest challenge, because it's very easy to say we're going to establish guidelines for geophysics, but it's such a broad field. So part of the initial focus is also to put boundaries on what are important topics and also what are important topics to be described in this guideline. So all of these subcommittees also focus on really describing these boundaries, where these guidelines are applicable and where not. So although there's a lot of different applications for it, I think by putting these boundaries, you make it a bit easier. A second challenge is, I think that it's a very new technique. I mean, the techniques are not that new, but the application, put it on UAVs, is very new, and a lot of people are doing very good work with it, but the wealth of information also means that there's not yet a general consensus. So this is also what we see, that some beliefs are changing quite rapidly because new information is gathered, and this is also one of the reasons why it's chosen to use a guideline instead of a standard, because right now you can still have the time to make changes, and a guideline is easier to update.
Thank you. And So Gary has a quick question, which is, will the guidelines be released under the auspices of an industry organization or just this group?
It is a very good question. We're in the process of collecting the affiliations, all the organizations that are wanting to support it, because we also believe, well, it's a community effort, but it should also be released by the community and supported by the community. So we're looking for as many geophysical societies as possible. For instance, the SAG is one of the supporting members for this. And with this, we hope of the widespread implementation of these guidelines. So yeah, that's a good question.
Great. Thank you so much for that presentation. So we'll continue on this track with our next speaker. And like I said, we'll have more time for group discussion at the end of today's formal presentations. So Tim Archer is joining us from Reed Geophysics, and we'll be speaking about guidelines for drone magnetic surveys. Take it away, Tim.
Thanks very much, Ken, and good afternoon, good morning, and good evening to everybody. Great to be part of this international forum. The previous speaker, Stephen, has really teed up quite nicely what I'm going to present, so I can skip through my first slides and go on a bit more about the technical detail. Thanks for that, Stephen. Stephen and I are both on the same committee, the International Committee with the very long title, and I just want to be clear, the work I'm presenting today is certainly not my own. I've had some input on some of the chapters, but it's very much been a team effort, and that's the spirit of developing these guidelines. So I'll just start with an obvious slide, which is what's not to love. Drones are everywhere. They are extremely useful in a range of applications, some of them slightly humorously shown here. And of course, with that enthusiasm, we can get carried away and start to make silly mistakes, either not listening to the science that's gone before or not applying it in ways that are novel and appropriate to the new technologies being developed. At this meeting 2 years ago, a committee was put together, or shortly after it. Inaugural meeting was November 2020. And the DMG there on the right-hand side, the drone magnetic guidelines, which is specifically what I'm going to be talking to. First draft came out in December last year, pre-final in September, and we're actually formally launching these guidelines, and some of you will have received emails about this already, on the 12th of next month. So just backing off slightly to the reasons for the guidelines, and again, I think Stephen's articulated these very well. Some of this is new, some of it is old. The technologies are old as far as they go, but the applications are new. And we need to understand the basics of good. We need to share information, and there are different learning challenges. This is the idea of different people coming either from the engineering space or the environmental or the hydrogeophysical or the exploration, even from petroleum as well. And bad data gives our industry profession a bad reputation. We want to avoid unnecessary restrictions, but we also want to respond in a responsible and professional manner to clients. And we want to create this culture of knowledge sharing. Obviously, we all have commercial agendas, and that's appropriate. But where we can, we need to pool our collective knowledge. And so the committee, again, the slide being presented, and I won't go through the detail. We come from a wide range of backgrounds and professional affiliations. And here's a slide that hasn't been presented before. This is where we're based as an entity, individual members. We're seeing some gaps. Let's see some contributors, please, from South America, from Asia, from China, from other parts of Africa. This really wants to be and needs to be a truly international effort if it's going to be successful. So back in March, we set up a bunch of subcommittees, and the agenda was ambitious. And we realized fairly quickly that these 8 or 10 committees were all going to take a lot of work. We're all going to be challenging to execute and implement. And so we took a view as a committee that frankly, the most evolved airborne technique currently operated on drones was the magnetic technique, and we had quite a lot to say about that. So we thought, well, let's get the ball rolling and set out the magnetic guidelines. And this is a sort of screenshot draft from August. But as I say, things have moved forward since then. Again, the aims just to underscore the point, this is laid out in the introduction to the document. And really, I think this has been touched on in previous slides. We want to engage the operators. We want to inform potential clients. We want to provide technical guidelines that are fluid as they go. and possibly move to standards, but that's less flexible and more onerous to implement. And then to provide references, kind of a go-to guide for people who want to dig in on the individual topics in more detail. So here are the draft contents of the MAG guidelines as at August, and they haven't changed a lot since then. There's a lot going on. I'm not going to grind through this in great detail. It's late on a Friday for some of us, later even for some. What I'm going to do is just take you through, I've made this point that these are going to be launched at a dedicated seminar. We're having a webinar on Saturday, the 12th of November, which some of you may think is a brilliant idea, and some of you, perhaps your families, may think is a terrible idea, but that's what we're doing. It'll be 2.5 hours, fairly short and sweet, and we're going to go in detail through pretty much all the items on this list. So please bookmark that in your calendars. If you've not received an email advice already, that is going to happen in a couple of weeks' time. I'm taking you now through the edited highlights from that guide, and mine is that luxury. Again, much of this work carried out by others. I've had a hand in it, but certainly not been the sole contributor by any means. Geomag 101, the Earth has an associated magnetic field, and that interacts with magnetic material in the subsurface and enables us to take measurements from the very shallow scale, unexploded ordnance and pipes within a meter of surface, through mineral exploration targets 200, 300, 400, 500 meters in, down to petroleum exploration at several kilometers. And we've got to think about the fact the magnetic field varies depending where we are on the Earth's surface, and we need to be cognizant of that when we're reducing the information that we acquire to information that can be useful. This is how the Earth, the geomagnetic field, H up at the top there, couples with buried magnetic objects, and so the interaction is quite complex, and because the Earth's field inclination varies depending where we are, so the observed field varies depending on where we are on the Earth's surface. And this is well understood and can be largely compensated for, but we need to be aware of it. The reason magnetic techniques work for geophysical applications is that different materials have different magnetic susceptibilities. This is the physical property that underlies the magnetic technique. And here's a useful slide, I feel, from a publication by Denheath and Mudge that summarizes some of these for different rock types. And of course, for ferrous material close to surface, they'll have an extremely large magnetic response. And that's good news when we're finding nasty things like electric cables and buried ordnance. The value of magnetics here is an example from Namibia, and what we're seeing is a reasonable geological map on the right-hand side, but a huge amount of detail revealed by the geophysics on the left, and particularly under the yellow shallow cover, where we're basically blind in terms of field mapping. Similarly, at the very near surface case, this is data from a test site here in the UK. And folk at the University of Leicester have buried fire extinguishers and oil drums and water-filled plastic containers and a whole bunch of things. And if you give them a call, you can go and you can test your geophysical equipment on site. And this is a magnetic image. So from the deep geology of Namibia right to, within touching distance of surface, the magnetic technique has genuine value. We unfortunately don't get the information for free. We have to process it, and typically if you've got an enormous great response, you don't have to do an awful lot to see the data. Top row here, an iron ore deposit with a huge multi-thousand nanotesla response. Bottom image, sedimentary basin, and you can see the raw data is awful to look at, and you've got to do quite a lot of detailed processing to get to a set of information that's useful. And so that brings up this next slide, which is depending how much detail you need, depends how much processing you need to apply. We're always careful, but you need to be even more careful if you want to extract the very subtle features. Sometimes that's helpful, sometimes that's not necessary. And again, some of the more dangerous features in the shallow subsurface do us the favor that they're highly detectable magnetically. This is important and new to UAV. Most of the processing corrections that we apply are self-similar to techniques that have been developed for airborne and ground magnetic survey for decades. Maneuver noise, however, is currently the main reason for drone-based aeromag surveys not achieving the high quality standards of conventional. And what I mean by that is we all appreciate that drones can maneuver around the sky, can be chucked around the sky both deliberately and by accident, or by environmental factors far more readily than an airborne and certainly a ground-based system. So there's a whole realm of discovery and experimentation and thought that needs to go into how do we get rid of, or at least suppress to manageable levels, this maneuver noise. Types of magnetic survey, again, a busy slide, and I don't expect you to read all of it, but just that we design a survey that's fit for purpose. If we're looking for shallow features with a high magnetic content, we can be more relaxed about noise levels than if we're looking for subtle features at depth. Line spacing as well. If you're far apart, you'll see deeper features, but you won't necessarily see shallower features. And these come into the survey plan, which is a key part of a successful drone magnetic survey. Survey design as well, just in brief, and there's more details in the guidelines. The guidelines run to 120 pages. So there's a lot of information, and I'd really encourage you to look at it, to attend the webinar if you can, and to get hold of the guidelines, which will be available on a public website if you can't. The bottom slide here just showing the obvious point that the deeper a feature is in the subsurface, the smaller the anomaly, and therefore the better the noise levels you have to find it. Noise sources are many and various, and I'll flick through those just briefly. This is an interesting slide for those of you familiar with looking at airborne data. The N4D, the normalized fourth difference, is a typical noise measure that we use for QCing, quality controlling airborne data. And what we find is that drone data often sampled at 1,000 hertz appears to be much noisier than conventional airborne data. If you resample it at 20 hertz, it calms down a lot. And that's a gotcha. If you're applying standard noise limit techniques to drone data, you've got to subsample it before. And that's not an intuitive result. Maneuver noise, I've mentioned already. This was a survey that was flown east-west, so the bird was swinging in the north-south direction. By bird, I mean the suspended magnetic sensor beneath the drone. And we can see direct correlation to the northing in green and the magnetic field. So if you don't think about where the sensor is beneath the drone, you're going to have noise in the data that's going to obscure your signal. Electromagnetic interference, intuitively, the closer you are to the rotor bleed, the instrument electronics on the drone, the more that's going to trouble your magnetic sensor. So the further out you can move it, the better from that perspective. But of course, the further out you move it, the more it pendulums beneath the drone. And so that introduces problems of its own. These are things to be thought about. Survey artifacts, and there's several. Good survey design can reduce and alleviate a lot of these. This is important. In conventional geophysics, airborne geophysics, we have what's called a figure of merit. You go up high and you throw the aircraft around the sky in a safe but fairly unpleasant manner. I've been on a figure of merit flight and it's no fun. But what you're trying to do is understand how the magnetometer responds to the attitude of the aircraft in the sky. For a range of reasons that I'll come to in a moment, that's difficult to do on a drone. And so one of our committee members has come up with a system that it's not difficult and complicated, but it's really helpful. You fly the same block, the same square, 3 times clockwise, 3 times anti-clockwise, and you have a look at, you compare the lines. Then if you are worried or you've got sufficient significant terrain in your survey area, you can build that into your flight plan. So you can create artificial terrain. It's completely safe. All you're doing is positioning the drone at a different point in the air, but you raise it swiftly, you drop it swiftly, and you pretend that there's a mountain or a building or whatever it is, and you see what effect that has on the data. We'd really like to see this as a standard operating procedure on a professional drone survey for magnetic measurements. Repeatability test. Technical considerations. This slide is deliberately tiny. There's good, solid information here about what to think about if you're commissioning a drone magnetic survey. I'm not going to go through it in detail today, but it's in the booklet. Compensation and calibration. I've talked about this a little already. For conventional compensation, airborne systems, you use the figure of merit, FOM. For compensating drone systems, WIP just stands for work in progress. Bulleted there are some of the reasons that you can't just apply a conventional figure of merit, and those matter. So again, the repeatability test in a previous slide is helpful here, and there's probably other ways to solve this problem as well. This is active research, and this matters. If we don't get this right, we're going to be collecting noise instead of signal. I'll say a little bit about vector magnetic systems, and not a lot, because it becomes fairly detailed. There are pros. benefits of vector mag systems, the cost, weight, and power. Vector magnetic systems, to be clear, we're measuring the components of the magnetic field in 3 orthogonal directions. With a scalar system, we're measuring purely the amplitude, the magnitude of the magnetic field. Disadvantages, we need very accurate vector calibration, 1/100th of a degree. And scalar calibration, there are scales and offsets and non-orthogonality and temperature. It can be done. It's not trivial. And I'll defer to others who know more about this particular element than I to give detail to those of you who are interested. Data processing, again, we borrow a lot of this from established techniques. So in green here, these are things that we know how to do and have known how to do for 50 years. What's not so easy, highlighted in red, is the compensation, and that goes back to the differences in maneuverability and field conditions for drone survey against conventional airborne. So again, an area of active work, and we welcome contributions from all sources really to solving these challenges. Again, the mess is moving left to right. We start with what's on the left, and with careful processing, we move to an image that is far more interpretable and far less prone to taking bad decisions. A little bit on imaging and interpretation. A little bit on data imaging. There's many ways to present geophysical data, and magnetics is no exception. It's all about emphasizing the features that you want and attenuating those that you don't. Think driving along on your car, you're listening to the radio, all of the channels are out there, but you move the dial to tune in into the classical music or the pop music or the reggae that you're interested in. Similarly with geophysical imaging and interpretation, it's all in there, but we're teasing out what we want and we're suppressing what we don't. Combining images in any number of ways, again, multi-plots, ternary imaging, relief shading, and of course going into 3D. Data interp, in this guideline, we've chosen to group this by 1D, 2D, and 3D. There's other ways to discuss interpretation. 2 challenges I'll speak about briefly. One is model ambiguity. This was a wonderful case study back in '87. And these authors presumably were getting annoyed with people pretending that their model was the only one that was right. So they modeled a famous mag anomaly under Lausanne, Switzerland, using a question mark, and made the rather facetious comment that it takes full account of the measured anomaly. From this point of view, it's considerably better than most of its predecessors. And also it's in harmony with at least one of the characteristics of the local geology. It's highly puzzling. But slightly less humorously and more seriously, we do need to think hard about the ambiguity of geophysics and mag in particular, and we use external observations such as geological observations to help constrain that, to reduce the myriad of possible ground responses to ones that are geologically and technically useful. The second challenge is that one I've mentioned already, that the dipole field means that the same block of ground, so exactly the identical target, has a completely different magnetic response depending on where we measure it on the Earth's surface. And this is well understood and we can get around it, but if we're not careful and if we don't know what we're doing, we're going to drill or not drill in the wrong place. So rain clearance matters as well. With a drone, do we drape? Do we fly constant elevation? The constant elevation, you're throwing the drone around in the sky, your noise levels improve, but you're probably not getting as much detail because you're not as close to the surface. I've spoken about 1D, 2D, 3D, and briefly there are pros and cons of both. I won't labor the point, it's in the book, in the guidelines. And then integrating, this is key. Let's not just collect geophysical measurements, let's work with our geoscience colleagues, geologists, geochemists, and others to build a holistic Earth model, whether that's for shallow investigation, for cultural interference, whether that's for deep investigation for minerals or energy. And all of these factors are important. Otherwise, we end up with this kind of ambiguity that I mentioned earlier. So drones are fantastic in very many ways. They can be flown for geophysical purposes, low, slow, they're adaptable and cheap. Data quality remains an issue. Legislative constraints such as BVLOS that we've just heard about earlier, payload and range. These are challenges that will be solved, but at the moment we need to be aware of them so that we can manage our systems for our commercial benefit and for that of our clients and the broader community as effectively as possible. How can you join the conversation? Well, you're here today. That's a good start. Don't forget to plug in at midday UTC on 12th of November, or write to me or any of the other committee members. We'd really welcome your input, both in terms of attending and possibly joining in, getting involved in the committee. If you've got expertise that you can contribute, we'd be very glad to hear from you. And thanks very much for your attention.
Thank you so much, Tim. That was packed full of information, and it's amazing to see the work that the community has put together and that the committee has done in the last couple of years. So we actually don't have any time for questions right now. I will point out that Lori posted a link to the webinar registration in the chat. So please, folks, be sure to check that out. And if you have any questions for Tim, please post them in the Q&A and Tim can answer them there or save them for our larger discussion. But I want to bring up our next speaker. So I will introduce them. So Ahmed Al-Raqmi is joining us from the Petroleum Development Oman. And they will be speaking to us about a novel solution to nodal seismic QC.
All right. Yeah. Hi, everybody. First of all, I would like to thank you all for the great summit. Really useful topics, for the drone usage, all the way from non-seismic data collection, UXOs, all the way to geohazards and BVLOSs. I already can think of many tasks we can actually, implement these in my place of work at least. So my slides will basically showcase the use of drones in seismic acquisition, specifically QCing the nodes in the field. So nodes are the equipment collecting data or seismic data or the energy being bounced back from the subsurface, in case someone is not familiar with that. So the outline for this, basically, I will just go over the challenges that we faced. Briefly, I would say our goals in terms of operations, and then also I would just elaborate more on the technology being used, field tests, and some of the optimizations that we're thinking of as a result of the operations that we are carrying out. And eventually, I will elaborate a little bit on the future uses seismic expression, at least for us. Honestly, this is more of a general idea of our experience rather than detailed results on what's being done, because we're running many tests. They're not really continuous. We run a test and then we do operations and then we run another test. So it's really hard to gather all the test results and then show them. At least for me, I would say. So a bit of background for those who are not fully aware of, the recent updates in the seismic acquisition world. So the seismic now, they're using basically nodes rather than the cable geophones. So some of those nodes are actually very smart in a way that they can communicate their status. When I say status, I'm talking about the battery, tilt, noise, capacity as well. So like the ones that we're using, the quantum nodes developed by Innova Geophysical. So the whole story is how to make sure that the nodes, they laid in the ground basically are in a very good status, in a good health. They are recording and you are not really working blindly, especially if you have huge number of them like we do. We have minimum of 30,000 nodes at any time in the field. For this specific project, we actually have way more than that. We do have around just under actually 50K nodes of quantum nodes, and then there's an extra 20K of other nodes. So those nodes are, the spread is actually being rolled over throughout a huge or extensive area, and for this specific project, it's actually more than 4,000K, 4,000 square kilometers of area. Starting with the problem, I would say our operation environment is actually challenging by itself. The deserts, mountains, hills, sand dunes, huge ones. Actually, I'm talking about 150 to 180 meters high. They're blocking the communication between the basically the transmitter, in this case the nodes that are laid under the ground, and the receivers, which in this case the gateways that they're receiving, the status of the nodes. On top of that, our seismic spread is actually huge by itself. Depending on the design or the seismic design, our average, scale is around 25 kilometers by 10 kilometers, and sometimes it's actually bigger than that, or it used to be actually bigger than that. And this spread is being rolled over every day. Part of it is being rolled over, so it's operating 24/7 throughout the year. It's not basically stopping. Furthermore, our standards and the client standards sometimes are a bit high. We allow very small percentage of 40 nodes to be available, to be in the spread. I'm talking about less than 1% of the 60K nodes available on the ground. Otherwise, we stop the operation as we consider ourselves working blindly, and we are losing actually a huge amount of money, talking about hundreds of thousands of dollars per day. And you're also jeopardizing the data quality, you know. You don't want to spend all that amount of money ending up with low quality data. So the basic, the main goals for us in BDO is basically to reduce the risk involved in our operations, given the fact that our operating seismic BGB crew has enough driving exposure risk already. So we aim to reduce or eliminate some of it when possible. And the node QC is an area, a promising area to basically remove or reduce around 25% or more of the driving involved, Meanwhile, you also achieve the QC yield that you are actually looking for. I've already mentioned how huge is the spread, so you don't want to let vehicles drive all the way throughout that spread. We've seen the undulating surfaces of that area. It's a very risky area. There are no pre-existing tracks on it. So it's a very high risk area. So, you're adding technology to the crew, that's in line with our goal of a smart crew, basically utilize the existing technology or evolving technology in order to basically produce more for less. And when I say this, it's not only less money, also less risk. In terms of technology used, so we are working closely with our friends in Innova Geophysical to achieve our mutual goals. So the nodes on the ground communicating their status using LoRa radio waves. The picture on the right, shows some of the existing communications technologies available now in the world. The extended range, of communication that LoRa offers is actually in line with our needs in our seismic crew. Given the fact that we have huge spread on the ground, along with the low, power consumption that LoRa, gateways are consuming. It's relatively low, which means that long flights are easily achievable. So you don't want to change batteries, or you have huge number of sets of batteries in the field. You just you want to do the QC over very small number of flights, basically. And with few bytes of data transmitted from these nodes, you will get your results, basically what you're looking for in terms of nodes QC. You'll make sure that most or 99% or more of your spread is actually healthy. On the other hand, the receivers, the gateway that also being developed by Innova has around, it's pretty small actually. It's around 750 grams. So it has around 16 channels in order for it to be able to receive the huge amount of the data being broadcasted from the nodes on the ground. The conventional way of the QC basically was to drive these gateways, 3 of them, well, that's what the average number of vehicles we have on the ground actually. So drive them over the spread on the ground on a vehicle, of course. However, the line of sight of the radio signals were significantly improved when we, elevated one of the 2 ends, either transmitters, in this the nodes, or the basically receivers. In this case, is the gateways, a bit from the ground, And that's logic in this case, because we do have all of these obstacles in the ground, including mountains, hills, etc. So we have done many tests to determine the optimum flying parameters using a DJI M300, and we tested all sorts of velocities, near 0 to almost 50, 60 sometimes, and all heights as well, from around 50s to 250 mainly. And I'm sure that at some of the tests I had 300 meters actually. And we noticed the increased reception range of the data. So many issues were solved. Currently we're spending less time to go over the whole spread and QC it, rather than driving just a drone flying over that spread. We overcome most of the issues when it comes to communication between the nodes and the and the gateway being blocked by the sand dunes or by the mountains. The good thing, I would say, we noticed that we are getting more new nodes per minute at higher speeds, which is very good. You don't want to fly your drone at 5 kilometers per hour. The fastest, the better. Of course, there's a chassis or more HSC risk involved, but then it's reasonable speed, and talk about somewhere between 25 to 30. In terms of height, we noticed after a certain time, after a certain height, basically, there's a minimal effect of how many nodes or how many new nodes being communicated to the gateway. And you can see here, it's a bit of crowded plot, but then that's the height of the drone, and then that's the cumulative number. And in dark blue, you can see the light blue giving you the number of new nodes per minute. But the takeaway of this is basically, after a certain height, you don't really receive so many new nodes. So it tells you that, okay, depending on the condition of the surface you're operating in, basically, in this project, for example, somewhere around 150 to 200 is the optimum height that you need to fly your drone at. If you go more than that, there's minimal effect. Actually, they're not adding anything, to be honest. So basically, that's the I would say the outcomes of the tests are really promising, and we implemented them in our operations. I actually wanted to show this video. I hope that works. Just one sec. So looking at this, this is an actual production results from the field. This is around 19 kilometers by 10 kilometers spread. We had around 9 or 8 flights. Each flight is around 30 minutes or so, at height of around 200 and cruising at 25 kilometers per second. So you can see, the number of nodes communicating their status to the gateways is actually, we can actually do, more sparser flights, but for us, we need to make sure that 100% of our, nodes are being QC'd. We just, put small spacing between these flights. So just to highlight, these flights are being done in daily basis, around maximum 10 or 11, I would say, 365 days a year. Our crew is operating 24/7, so we'll have, our standard says that they have to be QC'd at least once every 24/7. So you can imagine the number of logistics involved, the huge effort being done to do that using a vehicle rather than a drone. So the drones basically solve that a huge issue, basically. Maybe worth highlighting, we do face actually issues when it comes, to permits. Our projects are long-term projects and talking about, a year and a half. So when it comes to getting permits to fly a drone over a huge area for a very long time, it takes really time, but it does work, and we do overcome those obstacles most of the time. For the near future goals for us, so basically we are looking, to enhance the current the operations using drones for node QC. We are not stopping at this. Actually, we are working with Innova to produce a lighter weight gateway, which means longer flights than this set of batteries. Actually, we tested also, using these drones for aerial photography and then videography. So again, our surveyors have to plan for the next day operations. So rather than going to the site and visit the site, why they don't just use, the drones in order, to take some videos, photos, and then do the planning for the next day. Also, we are also looking for using drones for UXO detection, as some of the projects actually deemed required to use that. And actually, we are looking to do that for one of the next projects. Emergency response is one of the areas that we are looking at right now, and also non-seismic data acquisition. finally, I would like to thank our friends in BGP and Innova for their great support and commitment to make this work. Of course, also our friends in ISPA, they're the pilots that are piloting these drones. With that, I think I am done, and thanks for listening.
Thanks, Ahmed. That was really interesting. We've got a few minutes for questions, and we had a first question come in from Tim. Sorry, let me pull that back up. So the question is, have you thought about using drones for deployment of seismic nodes?
Right, that's a very good question. Right, so Tim, yes, in fact, actually we had many tests using drones to deploy the nodes, especially in the mountainous areas where we, usually you have the guys, the layout crew going with the nodes. It's very risky because those have some weight. So we actually had some tests, and we actually looking to redo more tests and redo some of the tests because we changed the node type that we are using. I would really appreciate if share your experience in that. But yes, it's an area that we are looking for. Especially that we are coming to one of some of the future projects are actually in a very rough areas. And we'd really need the drones to take some of the of that weight from the layout team.
Thanks very much, Ahmed. It's not a expertise of my own, but I know, for example, Total had the idea. We consult to mineral and petroleum explorers both, and they had a novel idea a few years back. So I just wanted your thoughts on that. Appreciate the challenges.
Right, thanks, Tim. Thanks.
So we had a couple other questions. One, I think this is a follow-up to your comments, and this is from Jean-Paul. And Jean-Paul, if I don't get this right, please jump in. Deployment like Total Energy's Menace project, very innovative. Thank you. Is the drone transmitting a diagnostic test results, or are you just pinging the node to see if it is active?
Well, so the nodes are broadcasting the status every, in our case, every 2 to 3 minutes. So there are two ways of getting that from, once they broadcast it to the gateway, then it's in the gateway. There are two ways of getting those data from it. First one is, there's a way that you just ask it to send it to our VCU, the vehicle control unit, or you just, wait for that drone to come back and then take the USB and then just plug it into your laptop. So both ways are available, but we don't really do anything. The nodes transmit or broadcast their status every 3 minutes automatically. You don't need to ping anything.
Thanks. So if folks have other questions, we still have another minute or so. While we wait to see if anyone else has a question, I was curious, did I understand you to say you're actually flying 24/7? And if so, I was wondering if you could just speak to your experience doing night operations. Seems like for a lot of geophysical surveys, that's one of the benefits of not needing light is to be able to conduct night surveys, but that also brings other challenges. So I wonder what your experience has been for that.
Right, I think I missaid that. So no, the operations are actually 24/7. So we do non-stop work, but in terms of QCing, we do that in the daytime. So we've got that window, but we have a minimum of 24 hours, QC. So we do that in the daytime when it comes to flying. We do actually have the same restrictions. We, when it comes to operation, it's pretty difficult to fly those or to get the permits to fly those, drones at night.
That's too bad because it would also address some of the potential temperature conditions
exactly
that you're dealing with. So, well, thank you so much. So I'm going to segue us into our overall discussion and summary. But before I do that, I just really want to thank all of the speakers for this morning, or my time anyway, in California this morning, as well as the whole week. So we have an hour set aside now for discussion. Folks are welcome to ask questions related to today's speakers, larger topics that have come up across the week. And as we go forward, Lori will be elevating folks so that everyone can turn on their own video and unmute yourself. However, we've been having some technical glitches with that this week. So there are, I think, about 65 folks on the call right now. And I'm going to apologize in advance. If you don't get elevated, it's not personal, it's not intentional, but we're having some technical issues. And if you don't get elevated and you want to ask a question or jump into the conversation, if you use the raise hand feature, which on the computer screen is usually at the bottom, there's where you have the share screen chat, there's a raise hand, and then Lori will be able to see that and unmute you. So folks are also welcome to just raise your hands if you have a comment or question, and Nathan and I will keep an eye on that list. But I will kick us off with a quick question. Well, it's not necessarily a quick question, but it's to the group of speakers today. One of the things that struck me was that the group of talks today really had a lot of synergy in terms of looking at applications of drone physics, flying in complex situations, and guidelines and addressing guidelines. And so I'm curious how the guidelines being developed handle the time sensitivity of applications with direct and immediate human safety considerations. For example, for an emergency sort of active slide, for example, or mine considerations or concerns, there could be the need for rapid analysis in order to provide data for use by first emergency responders, which is a very different scenario than long-term geophysical studies where we have sort of spaced out time. So I'm curious if how that's coming up with the discussions or about that.
Well, I guess I can speak a little bit about how things work in Canada here now. They've recently simplified things quite a bit. So as long as it's kind of the more like you're not flying in the controlled space of an airport or anything like that. It's a bit like I've got an app on my phone where I can quickly log in a flight plan, and as long as there's no like red flags on it, that will be fine. A lot of times, part of the issue with the really rapid response is also environmental. Like, here in BC last November, we had a lot of flooding, a lot of landslides in response to that. There was a lot of need for kind of rapid response, but also through a lot of that, it was still rainy and windy, which is not the best for flying a drone in. So yeah, there's always that side of it too, even when the regulatory side gets simplified.
Thanks, Andrew.
And I wouldn't mind speaking to beyond visual line of sight guidelines for emergency response. There is a regulation called BVLOS, or tactical beyond visual line of sight, that really refers to, say, an emergency fire, police activity, say looking for search and rescue. In those instances, they have some in the United States, the FAA has given guidelines to keep the aircraft within 1,500 meters, even if it's beyond visual line of sight, and still keep below that 400-foot threshold. So because we deal with also wildfires and hurricanes, other natural disasters, there are, call them geodomes or aerodomes, that certain responders are allowed to fly beyond visual line of sight for those specific purposes.
Thanks. Other questions or comments? So I see Ed posted in the Q&A, enjoyed all the talks today and this week. So this is a question about Xi's talk, but they actually posted they had to leave early since they were calling in from China, given the time zones. But they posted their email, Ed, if in the chat, and if you want to grab that and follow up with them directly. Other questions, folks, feel free to just raise your hand and we will keep an eye out for that.
Sorry, my question is for Ahmed. With the the DJI 300, how many nodes can you check in, say, in one flight?
Right. So I wouldn't be able to answer that, but I give you in total. So in total, we do have average 9 to 10 flights, more or less, give or take. But we do QC the full spread more. I would say 97 to 98 of the spread, and that is around a 30 or 38, I would say, 1,000 knots per day. So you can do the math. You can justify that by 9 basically, or 10, but that wouldn't give you an accurate answer. But again, because we don't really check, after each flight. Well, I don't do. Maybe the pilot does. But that's the status of every day's flights. I hope that answers your question.
Yeah, Ahmed, I'd like to piggyback on that question too, if I could. So those nodes, they communicate when you're flying over. They're communicating constantly, right? So you can check them. They all get checked, right?
Yeah.
As you fly over them.
Yeah, exactly. And the broadcasting frequency, you can't change it yourself. We set it up to 2.5 to 3 minutes. They don't do that simultaneously, but.
And the speed of the drone, I know you mentioned it, but what did you say it was?
So currently we are cruising around 25 kilometers per hour at around 200 meters high.
And just one more, at the end, your last slide kind of talked about future development. Is one of the things you're thinking about maybe a fixed wing drone with maybe a beyond visual line of sight type of operation? Right.
So Innova, they're looking at that. So I believe once they have something, we are always happy to test that in our field. Currently, we are using what's available in the contract, because we are using another company to fly the drones called ISPA, and they don't have the fixed wing yet. So they're both working to get that fixed wing, either to get it licensed to us, or fix the gateway on it by Innova as well. So yeah, that's something we really look into it. Yeah, that seems like a great application for fixed wing, just with places without trees, and you can keep not flat, but not mountains. So anyway, thank you. Thanks for the comment.
Yeah, so just a follow-up question. In terms of placement of the geophones, are they in a small array, one small array per node? And is it all manual placement and pickup, or are you using drones to place the geophones or the nodes? Because I believe there has been some experimentation with that in certain areas. Could you elaborate on that, on the actual placement of the geophones and systems and the node boxes, etc.?
Right. I didn't really get the first question, but the second one, we do that manually. As I said before, we had some tests to deploy them using drones, but we stopped. It was just before COVID. And after that, we actually changed the nodes that we're using. So we'll have, all the previous tests wouldn't really, work, because you'll have to, the payload now changed, the size of the nodes, the weight of them changed. So we'll have to redo some of those tests. And we are really looking, to find that opportunity to do it. So currently we are using, deploying them manually.
Please just raise your hand if you have a question. And so I actually have a question for Dan. I was really curious in terms of the beyond visual line of sight, looking at that sort of hazard assessment chart, considering that flying in agricultural areas or sort of remote rural areas, that some of the hazards are considered less. And I can see that if you're thinking of the drone, if someone's thinking of the drone crashing, that there's, fewer people and infrastructure there. But in my experience flying, for example, in the Arctic National Wildlife Refuge or just in agricultural areas in Northern California, is that the aerial hazards can be more complex, because I encounter more fixed wing aircraft or rotor aircraft flying below the drone, often hugging terrain at quite low altitudes. And so I was wondering if you have any thoughts on how do we, and especially when you think about, and I was flying at, 300-400 feet or higher, and especially during the conversations that we're having this week, when we get into some of the geophysical sensors that are flying usually low as well, so that adds in a whole other level of complexity. And I was wondering if you had any thoughts or comments on that.
Yeah, that's you hear of these instances pretty often, even including helicopter encounters, because they can fly at a lower altitude. And especially in rural areas, this is where you see a fair number of these drone encounters that the FAA reports, and they're on the order of hundreds per year. And it really points out the significance of remote ID, the ability for pilots to produce a NOTAM, a notice to airmen, saying that this is their area of operations, and this should be something that manned aircraft pilots are checking before they take off every single time. So this is a complication with introducing drones into the airspace, and it's something the FAA is trying to address with remote ID, with the more routine addition of NOTAMs or DROTAMs, we sometimes call them, the drone notice to airmen. But it really does emphasize that with that chart I showed, where you have good communication and low autonomy in rural areas, it doesn't exclude communication. It says it's good or better. So communication with other airmen, like I was saying, through NOTAMs is essential. But also what plays into that is the autonomy, the ability for some sort of system to detect and avoid aircraft in the area. The last thing I'll say is that ADS-B, that signal broadcast that comes both from the drone, and not all manned aircraft are required to produce that ADS-B signal. But that's something the FAA is looking at, to require every aircraft in the air to produce that signal, so everyone's aware of their position in the air.
Thanks. And I'll just add that, I was flying in an agricultural area recently, and the aircraft were flying over fields. There were helicopters flying below the tree line. And I was talking to one of the local farmers who was also a pilot, and I, was talking about NOTAMs, and he literally laughed and was like, nobody out here would actually bother to look at a NOTAM. So there's what we optimally expect our, aircraft pilots to be doing. And then there's also sort of the real world scenarios that we're operating in. So I find it interesting and challenging. So Nathan, did you?
I just want to say I agree with that my experience has been that, when we do our operations, we fly the NOTAMs, but they are not, I've never had any evidence of them being checked ever by any planes or anyone. And it's a due diligence step right now. And Dan, you were right about, maybe DROTAMs could be more emphasized, or something more integrated with manned aviation operations, where they get used to checking them more or something. But yeah, those, and also to add on to that, so I actually have a question. So the manned aviation, planes and stuff, they're supposed to have a transponder on them. Is that right?
It's not fully required. I think you would need you need certain instruments to fly in certain airspace, but for general airspace, Class G, that we mostly fly in, it's not required.
Okay. Well, then never mind, because we ran into a lot of planes that would, fly really low, and they'd come over a ridge, right into our drone operations in the drone airspace. But we didn't have any way of knowing that they were going to be there. And we, we're checking different apps and stuff, and they weren't on there either, which other aircrafts were, but those weren't. So we had to really keep an eye out. I had to drop what I was doing and go to another location and just be be a visual observer for them and make sure that, once those planes do come over that ridge, that we avoid them, that we basically drop the UAV down. So,
right.
Yeah.
And that is the prerogative of a drone or an unmanned aircraft, is to yield to all manned aircraft, regardless of what's going on. And it even allows for the ability to go above 400 feet AGL if need be. For any emergency procedure, you can do what it takes to yield right of way. But also just speak personally that I totally agree. I think the FAA is trying to appease all parties by not requiring manned aircraft to all buy this expensive sensor and produce ADS-B signal. But they're also trying to enable the drone industry, and their way of meeting in the middle is detect and avoid systems that are reliable. And I've experienced this personally when doing BVLOS flights of an aircraft that even was producing ADS-B signal. We could see it coming, but by the time our visual observers could see its orientation and tell where it was coming, it was a matter of seconds before we had to make a decision on what to do. So it requires vigilance, and that's you can't take that away. That's for sure.
Wow. And those acoustic sensors that you kind of showed for a second that would actually detect the sound, that was incredible. I don't think I've seen those before.
Yeah, that goes back to maybe the earlier days of BVLOS. And I say earlier, I'm saying like maybe 2017, 2018. Precision Hawk had developed this system, before there was any sort of visual sensors that could be out there, and radar just wasn't developed well enough. I thought it was a novel approach, but you don't see it as often anymore.
Thanks. So we had a couple other questions. So Tim, do you want to unmute yourself and just jump in and ask your question to the larger group? And while Tim unmutes, Dan, there was a question in the Q&A. I'm not sure if you saw it, about extended visual line of sight. So I don't know if you want to answer that in the Q&A panel.
Sure.
Yeah, thanks. So I'll jump in on that. Apologies, I can't post in the Q&A, but I popped it in the chat. Also, I've not been able to attend the entire summit, so may have missed with this question. Just a question really for everyone. What do we think are the burning challenges facing the drone geophysics community at present? And I think peculiar to our sector, there's obviously challenges that we borrow from others, BVLOS being one of them, and public awareness and safety generally, but are there peculiar challenges to our industry? And again, we've got a lot of people on the call from different parts of the geophysics community. Be glad to just people pile in and say, what do we think of the challenges? And then I've just added, challenges almost always create opportunities. So if we want to speak to the opportunities as well, that'd be great. Bit of a vague question, but hopefully stimulate some discussion. Thanks.
Well, Tim, I can jump in there and at least address from my perspective. That if you had to break it down into two main focuses, it would be the data and then the operations, right? So on the operation side, I would say one of the main challenges is payload weight, payload size. Since these geophysical sensors can get pretty heavy, I think the UAV industry is still catching up to what the size of these sensors are. So with the mag arrow, there's the MFAM microfabricated atomic magnetometer that is very lightweight, but it's also very sensitive. So maybe in the future, I know we're looking at making these sensors smaller and lighter, and then on the other end of that is making the drones bigger and able to carry more weight and still maintain some sort of flight times that make it feasible.
Yeah, thanks. And I think we're going to see that again coming in from other sectors, aren't we? And we can use that technology, but certainly, heavier payloads. I'm an EM kind of guy. I'm a gravity kind of guy. And gravity brings its own peculiar problems in terms of accelerations and such. But yeah, definitely, if we've got a bit more payload, we can start to do smarter things. I guess I'm in favor of semi-airborne EM systems for the minute, just as a more practical, but maybe in due course we'll see them fully autonomous, fully airborne. So yeah, thanks for that.
Yeah, I guess kind of on the same theme of that, I think there's a lot of opportunities coming up with, yeah, if we can get these larger payloads coupled with smaller sensors, getting more of the, kind of multi-sensor systems going. I know, said not being a real geophysicist, but end user of some of that data. And I've seen like really good stuff doing, sorry, my, everyone is trying to contact me on Teams at the same time now. Some really good stuff doing like rock slope characterization from terrestrial setups using, combined LiDAR, thermal, and multi or hyperspectral imagery, where you can kind of pick out the structural geology side of things, plus zones of alteration that could be causing rock slope instabilities, those kind of things. Mm-hmm. But then always the challenge is you need a spot where you can set up a tripod where you can see all of these things. So being able to get more of those like multi-sensor systems practically into the sky would, I think, be a big benefit from the more geological engineering side of things.
Yep. Yeah. How are we doing on hybrid systems? So better range with petrol engines and good things like that.
I've seen them, but I've never actually used one, so I don't know.
I can answer that. I used the big thermal engine drone, but it was like 25 kilo, and it fly very long. But the price of the drone itself started at between $100,000 and $200,000. So with this kind of price tag, I'm not sure it's beneficial to use this kind of drones compared to manned aircrafts. I'm talking about only about magnetometry now because it's what I know. And to go a bit further on the topics we're discussing, for heavy payload, maybe it's might be a interesting way to do it, but for some application I think it's good, but for some other, when you go close to urban areas or when you have to deploy your drones in remote area, I'm not sure that getting bigger is for some application is the best, and I will advocate for getting smaller with smaller drones for one application at a time, and to a bit like what I presented a few days ago with like below 2 kilogram system that will be less prone to winds, for example, and so on, and that can be carried on a flight, on the plane, and so on. So I think different approach have to be developed according to the regulation and your application to application. Yeah.
And again, I think we're going to see, as you pointed out there, Bruno, sort of segmentation of our market, aren't we? So there'll be heavyweight drones for particular applications. There'll be others where, as you've pointed out, small, nimble drones are going to be far more cost effective. And we're going to see a sort of a segmentation within the market as we do in so many other areas. But no, that's helpful. Thanks.
I will say for close to ground, like when you want to replace ground-borne surveys, you want to fly at 1, 2, 3 meters with multi-sensor or like multi-magnetometers or GPR, like we saw before. You want to go bigger, but when you want to do larger survey for geological application, for example, maybe you want to have smaller things, like as you said, depends on the aim of the survey. Yeah.
One thing I'll add, so working with the U.S. Department of Interior and the U.S. Geological Survey, I get the privilege of working with literally hundreds of pilots flying all across the United States with a wide range of geoscience applications. And one of the things that consistently stands out to me, working like I work with GPR, and we've got folks working with magnetics, but I've also flown, multispectral and optical and thermal IR routine hydrological studies and for hydrogeophysics surveys. And one of the things that really strikes me with the traditional geophysical sensors is that right now, when we're looking at other geoscience applications, people are typically looking, how high can we fly? And the actual sort of aircraft doesn't impact the actual data quite as much. So it seems like there's a different suite of considerations when we're talking about challenges of geophysics. There's, in terms of potential noise from the aircraft itself, and not just the motion, but the electromagnetic potential interference of the aircraft on the data. And then also just, we see more, just looking at all the presentations this week, we see more sling load payloads, which is a different skill when flying. So that's very different than flying a small, hand-sized quadcopter with a camera mounted to it. And then we are also, hearing lots of folks talking about flying low. And that's a completely different skill set in terms of flying low than versus an automated survey at 400 feet or higher or something. So that to me is a big challenge. Jeff, did you want to jump in?
Yeah, one of the things, Tim, that came up yesterday was this problem of the sling loads. Ron Bell, for example, has managed to suppress the swing of the sling loads by using, sort of a semi-rigid four rods going down and then having a stabilizing influence about halfway down the suspension. But for a lot of the sensors that we saw that are under development, the problem of getting that stability in the sling load when the drone's starting and stopping or being manually flown is a problem that's going to prop up for a lot of sensors. That you want to have a nice smooth progression of the drone, nice smooth progression of the birds. And so I think that's just a mechanical challenge that a bit of work needs to be done on the suspended loads by the look of it.
Yeah, that was the compelling slide in my presentation. I don't know if that was Reiner's or Paul's, showing that the direct correlation between the bird swing and the magnetic field. And I think the first thing we need to do is be aware of that as a noise source and then figure out ways to address it. I remember my early career with Anglo American, and we spent an awful lot of time, I was with their airborne EM system, working out how to suspend the receiver coils within the towed bird because of the effect it had on noise levels. So Kian, these solutions are forthcoming. And again, let's not completely reinvent the wheel. Airborne geophysical platforms have been flying slung loads and towed birds for decades. I really think we can learn from some of that. And there'll be novel solutions as well, like Ron presented earlier this week. So, yeah.
I had a question for Dan Bochicchio, if he's still on. From what I understand, Dan, you've had some experience with a magnetic sensor that is it's hard mounted on and then it's got like a swivel, so when you land it, you can still land. So it's still a slung load, but it's hard mounted, so it's like a rod. Is that right?
Right. Yeah. The way we describe it is like a hanging Q-tip, and the juncture between the aircraft and that sensor is kind of the interesting piece there. That using a sliding lock, we're able to put this sensor into a knuckle that is only allowed for, think of it as roll and pitch. So there's no yaw, which is an interesting element to remove from that noise when you have that swinging load underneath. There are some maybe drawbacks to this style of payload suspension where hanging multiple arrays or a multiple array sensor gets a little more challenging. You think of a T-shape, an upside down T-shape under that. But by removing that yaw from the sensor, it actually increases the accuracy quite a bit. I think it would be something that it would be interesting to see others kind of build on this idea.
So when you land it, so when it takes off, it's connected to the drone, right? And the joint allows it to, whenever the drone comes up, basically the sensor and the rod become vertical.
Right. Yeah. Talking like a true geologist with your hands now.
Yeah.
And Right. So because the sensor can shift forward and back, kind of pitching forward and back, if you were to maybe strike an object like a fence or a bush, the sensor can freely swing backwards and it doesn't damage the sensor, especially since you're flying low and slow. And when you're finished with the flight, that's where we have a lock and pin mechanism. So we use a little foot pedal in order to trigger, and it's really just a servo motor with a small Arduino attached there, and it has just a small transmitter on there. So we can hit the foot pedal and drop that sensor into a net once it's low. And we haven't automated that step, but requires some manual flying to position it over the net, drop the sensor, and then go land.
Gotcha. Very interesting stuff. And as Tim said, that may be reinventing the wheel, or maybe it's done before. I'm not been done before. I'm not sure, but yeah, really neat. I've been curious. I was always curious. How did they land that? Okay, it detaches. All right.
Dan, I'm curious, is there a reason to not just leave it in a fixed mode the whole time? Because I know, for example, for some gas airborne UAV surveys, they are extending, sort of that Q-tip kind of shape, but out in front of the aircraft to get it out of the prop wash. And so is that a potential solution?
Well, like with many other sensors where you can try to subtract the noise that's created from the electromagnetic noise created from the motors, hanging the sensor, what is it, about 1.5 meters beneath the drone seems to mitigate that. But the orientation of the sensor, I mean, this was really just our first iteration, and I can't claim to be the chief designer on that. But having seen the later designs and other iterations on it, I think the really depends on what type of target you're trying to characterize. Whether you want a horizontal array to cover a wider scan area, or if you're, say, using a series of gradiometers to, this is getting beyond my geophysical knowledge, but if that T-shape is not horizontal but in front of you, it might just be trying to get more detail on a small area and particular targets.
Thanks. So I'm going to raise another question, and Callum, I invite you to jump in because this is something you raised earlier this week. The question relates to this topic of whether there's a sense of a need or an interest in specialized drone development for a particular suite of geophysical sensors. And I also just want to reiterate and invite everyone to feel free to jump in with your questions. Just raise your hand if you have a question or a comment, or if you'd like to reply to one of the questions in discussion.
Yeah, I'd say one of the things I focused on throughout my PhD research was kind of looking at these electromagnetic signals and trying to, characterize them so people can go forward and find ways to compensate them from the surveying that we do. And one of the things I've kind of toyed with in the back of my head is trying to talk to a drone manufacturer and seeing if they can, create more of an optimized drone that will actually be used more so for geophysical surveys. So things with less electromagnetic interference and stuff like this. So that's one thing I've been looking to move forward with. And part of the research I want to do is probably looking at this as well. One of the other things I want to point out is just, myself being from an academic background, but also, talking with a lot of people that are more kind of the end users of this. I think one of the things I want to try and do is just kind of disseminate the research that people do, kind of the high level stuff, and, make people more aware of what's out there and kind of the advancements we make from a characterization standpoint to people then, creating processing methods and stuff like that that can be used. And so I mean, the paper I posted is just kind of helping with that, where someone took a lot of the research I worked on and then created a compensation algorithm based on that.
Thanks, Callum. Tim, see your hand.
Yeah, thanks, Callum. I'm aware, folk, of one particular drone manufacturer that worked pretty closely with, I think, the Mag Arrow team to develop a drone that was as magnetically invisible as possible. I can give the details. I won't share it in this forum, but give the details to anyone who's interested. And there's benefit to that. You know, we see, so my bag really is airborne QC, and we see the better surveyors in that space really A, rewiring, B, deriveting, C, demagnetizing their entire airframe just to get the magnetic noise floor down. And then we still do the compensation as well. So again, lessons learned, I think, from those who've gone before. Clearly a drone is a different animal to an aircraft. And as I mentioned in my presentation, the movement, the range of movement available to a drone is far more spectacular and therefore troubling than a conventional airframe. But I welcome that kind of thoughtful, specific demagnetization of a drone platform. Thanks.
Thanks, Tim. And Bruno, I see you have your hand up.
Yeah, I had about this demagnetization of the drone platform. Wondering how you can deal with noise from the rotors, like the engine, because it's what I've found the most difficult to correct, because noise from electromagnetic, very high frequency noise, you can always filter, like not always, but it's easier to filter. But the noise coming from the rotation of your engine, because it's big magnets, and it's changing through time according to your speed, to if you have some variation of topography, it's quite a challenge. So how could you manage to reduce that, in your opinion?
One of the things that I've been looking at is, you know, characterizing them. And of course, as you said, the magnetic interference is related to, you know, the rotation frequency, which interestingly enough, I found only varies, you know, not that much in RPM terms. So in hertz, you know, you're looking somewhere between 40 to 60 hertz throughout the entire flight most of the time for when you're collecting the magnetic data. Obviously, what most people do is suspend the magnetometer below it. The closer you bring it up towards those motors, the larger those signals are. And I'll point out in one of the papers that I wrote, the signals they start at around 50 hertz and then they get higher and higher up into the kilohertz frequency, just due to a number of different factors with that. So actually what happens is you can get these being aliased into specific lower frequencies within the data, which can be rather challenging. Yeah, I don't know how we kind of fix that other than if you try and shield those motors with something like mu metal or something like that, but it's not obvious to me how you would be able to do that. So I think that that problem is going to persist for a while with drone magnetics, particularly unless some new type of engine is developed or someone can find a way to kind of balance out these rotor signal noises. So I don't know, that's just some thoughts on my end about it, but there's definitely a huge body of work that's been done on this from a number of different researchers, some who have talked here that explain this in a little bit more detail, but it's a big challenge.
Again, on the airborne end, two things get done. One, you minimize the footprint by the techniques I've mentioned, and two, you still have to fly or apply a compensation algorithm. So that's a fairly complicated numerical surface in N space that you generate largely through the figure of merit test that I mentioned earlier. So you compute the aircraft's effect in pretty much every conceivable attitude, pitch, roll, yaw, and then apply that numerically to the data. It's very effective. And again, I think we can do, I'm sure Callum, you and others have already been thinking along those lines, but let's let's borrow that technology and apply it as fully as possible in the drone space.
Tim, since we're talking mag and the guidelines are coming out, I had a quick question about the guidelines webinar. Will the draft guidelines be available before the webinar so folks can review them and then speak to them during the webinar, or are they being launched at the webinar and people can download them afterwards?
Jeff, I guess I'll let you pick that up.
Yeah, we're hoping to have it. The website is in the process of being built, and we want a secure way of downloading and then uploading corrected versions, because we want to encourage people to upload corrected versions. So that's all got to be sorted out. We're hoping that around about 4 days before the webinar, a copy of the guidelines will be available for download. That's the hope. The worst case scenario is just what you've mentioned, that it won't be available until the time of the webinar or the next day. But we're hoping it'll be 4 days before.
So we have another maybe 5 minutes for discussion before we have a closing. And are there any other burning comments, thoughts, questions? And I invite, this is a community discussion, so I invite all the participants, if there's something on your mind or a comment you want to follow up on, to just raise your hand so we can call on you. So in the interim, Jeff, you have your hand raised.
Yeah, just a supplementary comment. If everybody goes in and registers as soon as possible, then I think we'll work out some arrangement whereby either they can go back to the registration page and find out when the guidelines will actually be posted and what the link will be, or Laurie might organise a mail out to all the people that have registered. So register early, and then the notification of when the guidelines are ready for download will probably get to you one way or another.
Thanks, Jeff.
Yeah, I can say a few words in closing and just thank everyone for joining us for the 2022 Summit on Drone Geophysics. It was, a wonderful time again this year, like the previous years, and lots of fascinating talks and great presenters. And I want to specifically thank every one of our panelists that helped run each of the days. So yes, thank you everyone for attending. And we will probably be, if you're interested in helping out in next year's Summit on Drone Geophysics, we're going to be forming the technical committee for that coming up soon. So please reach out to myself or Laurie or Laura, and we will be happy to include you in that.
Yeah, no, Callum, I just wanted to reiterate what Callum just said. It was an amazing conference. Yeah, we heard about everything from exploration to hydrogeophysics, to UXO, to geohazards. And it just shows there's a lot more development that can happen in the field and what great progress we've made. So it's really exciting. I know I do a lot of UXO work or help people process their data. So to see that being done on drones is amazing, and just to see where we can go with that. Yeah, and I just really enjoyed the last 4 days. I'll pop my email in the chat as well. Yeah, so to join the technical committee for next year, please contact us. Yeah, and I think that's it. Keen or anyone else want to add anything?
I just want to give a shout out to Laura and Callum and Laurie for all the heavy lifting that has happened, and the success of this event is owed to them and to all of the speakers. So big virtual round of applause. We don't have the reactions menu, but we're all clapping. But thanks.
And thanks to the wonderful technical committee as well. That was a great group this year.
Well, great. Then why don't we close out today? And I'm guessing we will all see a lot of each other at the November 12th webinar. So big thanks to everybody and have a great weekend.
Thank you all.
Thanks, everyone.